So yeah, let's start. There is plenty of material today and only short time. So let's see how much we can fit in. The goals of this class or lecture is basically to start by telling you what parsing is and why do we care about parsing. And actually, I think this is the most important part because most of you may not end up implementing parsers, which is the rest of the topic, but you will be hopefully using them or hearing about them. So it will be kind of useful to know why they are good for. And then we'll be talking about two kinds of syntax representations. One of them is phrase-based, which will be the first half, roughly, and then dependency in the second half. And in each of them, we'll talk about how to parse with these, or how do we produce these trees automatically. And again, if you are not if you're a bit too tired to get into the details of how it all works exactly, it's also fine. But try to keep pace. And as I said, there is plenty of material here. Usually, I take 3 times as more to cover all of this. So I remove some stuff away, and I'll talk quickly. And I think it will be fine. OK, so what is parsing? So sentences in language have structure. Okay, and linguists, what they do is to create linguistic theories for defining what this structure actually is. And the parsing problem is recovering this structure. Now, I'm not saying that we know what this structure is, because linguists keep arguing on what the right thing is, and they keep changing their minds. But they all agree on some kind of common grounds, which they call the boring stuff. And I would say that this boring stuff is already quite useful, and that's what we are focusing about. So I'm not teaching you any linguistic theory, but how broadly these things look. Okay, so the idea about parsing is that you take a sentence like that, and then create some structure on top. Okay, and you have to basically go from this to this. What is the tree around this sentence? And this is called a phrase-based tree or a constituency tree. So each group of words is grouped into one unit, and you have some hierarchy there. And there's also dependency parsing, where you start from this and go to this one, where basically each word depends or modifies another word. Okay, so that's the task. And now you may ask, OK, why do you need these trees? Let's think of some tasks that you actually want to perform, okay? Like sentence analysis. So you want to know if the sentence, the soup, which I expected to be good, was bad, is positive or negative, okay? And you can look at this and you say, OK, so it's negative, but how do you know? So there are 2 words here, good and bad. So that's not really telling you anything. And good is kind of closer to the beginning, so maybe it's more good than bad, or maybe not. We don't really know. Okay, so it's really hard to say. But if we have this parse tree on top, okay, we can see that there is a very kind of close connection between soup and was and bad. Okay, and that good is kind of buried somewhere there in this tree. So if you have this extra structure, you get better knowledge of what relates to what and what's important or not. Okay, so this can help in sentiment. Okay. And also, when you're doing translation, this is work with my student Roy. So you can do MT, and there are many ways to do it. And here, there is some system that translates from German to English. And it does well, but not great. And we managed to have a better translation. And we did that by predicting not only the words, but the words and the tree on top. Okay, so if you make the system translate into trees and not into just strings, it somehow learns to do a better job. Okay, so if you know how the sentence is structured, you can also translate better. And here this is another work where we basically want to go over a lot of text and extract stuff. So we want to extract facts like Tuvalu is a country, Ninjaken is a weapon, and so on, just by reading text. And there is quite an elaborate system to do it, which I will not describe. But the way it works in the beginning is that we have this sentence, okay, and we parse it, and then we look at the tree path between these words, and then when we have this subtree, okay, we do something with neural nets and some other thing, and basically half of the system is based on parse tree paths. Okay, so I did not describe how it works, but you can see that it's a component of this other system, because it kind of tells you how the words relate to each other. Okay, and we can get very nice results using these dependency trees. And also here, so we have this task where you want for the word for to know what it indicates. Okay, and again, there is this kind of elaborate system over there, but if you look at that part, so that part is a classifier with features, and if you look at what the features are, then many of them are derived from the parse tree. So again, I will not go into this into the details, but basically, if you have a parse tree, you can start asking questions. Okay, so this word, what is its parent? Who are its children? And so on, like what is its depth, and these things are informative to other systems that you can just plug in as features. Okay? So parse trees play a central role in many, many applications. I will not go into more detail about that, but basically, I hope I somehow managed to convince you that this is actually useful for something. So like no person wants to have to see a parse tree. Well, some do, but like no customer of anything wants to see a parse tree, but it is very essential for many other things that people are trying to solve as a component. Okay, and some other nice thing about syntax or parsing is that you can actually recover this structure without understanding the words, or with only knowing some of them. Okay, so if you see this sentence, the plumpets and the grooms grokked the gulp, which you don't understand because it's not made of real words, okay? But you can still know that like there is something called the plumpet, and there is more than one, and there is a similar thing called the groom, and then these are together, and there is an action called gawking, and you can usually kind of infer what the structure here is, and automatic parsers can also get it right, okay? And that's nice because it means that you can learn from relatively few data, because you don't have to know what every word means. You just have to know how the words look, roughly, or like what their tags are, okay, what are the part of speech. And then it can run and parse words that it doesn't really know very well. And then you can use these parse trees to learn more about the words. Okay, so that's a nice property, that you don't need to understand the words to parse well for most of the time. So of course, there are cases where you really do need to know the words, but not that many of them. Okay, and now let's relate all of this to yesterday. Then parsing is just a case of structure prediction, where you have some input, which is a sentence, and you want to produce an output which is complex, like a tree. Okay? And previously, like yesterday, your structure was a sequence, and each item in the sequence can be tagged. Okay? And maybe we can mark some spans for any R, something like that, but that's it. And what we have today in parsing is that we have some hierarchy. Okay? So it's a more elaborate structure. So what's hierarchy? So I guess you know this thing, like math. So you can take this expression and think of it as there are like two things called multiplication and then an addition, okay? And you do this and then you do the other, okay? And you can also represent it like that, maybe, without these extra symbols, where each symbol from the formula is its own meaning, basically, okay? And it also happens in language data. So if you look something like that, fruit flies like a banana, then you can see this structure. So a banana is something called a noun phrase. Okay, like a banana is something called a verb phrase. Fruit flies is also a noun phrase, and then there is the sentence S, which is all of them together. Or you can have that other structure on the other side, where you have the word like, which is the main thing, and what like, so flies like banana, and then which flies and fruit flies and a banana. And this is called constituency structure or phrase-based structure, because there are phrases there that we kind of group together. And this part of the class will be about this kind of parsing. So how do we map between sentences and trees like that, which have like labels on each span of the sentence? Okay, so why is this hard? So it's hard because what we call ambiguity. Okay, so if you look at the sentence, fat people eat candy. Okay, so you see the structure. So there is a noun phrase and a verb phrase, and fat people is the noun phrase, and what they do is they eat candy. Okay, and then you can look at a slightly different sentence, okay, which is a bit trickier for people to understand, but give it a minute and you'll figure it out, maybe. So the structure here, so the thing here is that accumulates here is not a noun, it's a verb actually, okay, and then it's a very similar sentence, but it has a very different structure, okay, and this one says that the fat that people eat accumulates, okay, so here people eat is some kind of an adjective phrase, and fat is the main noun, and all of this together is noun phrase, and then accumulates is the main verb of the thing. Okay, and this guy is confusing also for people most of the time. It's called a garden path sentence because you read it, and then you get to the end, and you get stuck, and then you reanalyze. Okay, unless you know it already, and then you don't get stuck. But like most people get stuck on the first read of this. Okay. So this is hard for both human and computers, and maybe even easier for computers because they don't have these expectations like that human do. But for most other sentences, computers find many differing analyses which people even don't see, but which are kind of confusing. So on the same or on very similar structures, you can have very different trees on top. Okay. Or like even think of this, so I ate pizza with anchovies and I ate pizza with friends. Here it's the kind of same post tags, okay, the same, pronoun and a verb and a noun and a position and a noun, okay? But the structure there is different because when you eat pizza with anchovies, then the anchovies are part of the pizza, okay, usually. And when you eat pizza with friends, then the friends connect to the ate and not to the pizza, usually. Okay. So yeah. So there is ambiguity here. And another case where parsing is hard is just like real sentences are not, like 5 words. They are like that. Okay. They are much longer, and then you have to assign a structure to a much longer thing, and then there are many more ambiguities and many more options to get it wrong, and you just have to cover many trees to get the right one. Okay, so now we know what is parsing, why it's interesting, I hope, and why it's hard, I hope. And now let's see how to parse. Okay, but first we'll review some stuff from automata and like from languages. I'll do it quickly. And that's context-free grammars, which are essential to this part of, to this kind of parsing. So context-free grammar, like anything in automata theory, is an n-tuple or a 4-tuple. So we have a set of non-terminal symbols, and that's the things in the tree, okay, these NP, VP, S labels. We have an alphabet of terminal symbols, which are the words at the bottom of the tree. Okay, we have a set of rules. And the rules are basically saying there is a left-hand side and a right-hand side, and you can, and the left-hand side is one thing, and the right-hand side is 2 things or more. Okay, and then and the rules are composed of these and these. Okay, and there is S, which is a special symbol out of those. Okay, so let's see an example. Okay, so we have here. The non-terminals are S, NP, VP, and so on. Okay, usually there are more, but like here we'll have this toy example with a few. The vocabulary or the alphabet is these words. Again, usually there are like many more because language is much more diverse than 1, 2, 3, 4, 5, 6, 7, 8 words. Usually we have more words than that in our vocabulary, but let's say that it is. S is the S symbol, so that's the kind of special symbol. And then the rules look like that. Okay, so S can derive NP, VP. NP can derive adjective noun, NP can also derive determiner noun, VP can be VB and NP, and so on. And then we have these rules, which I call lexical rules, because it basically goes from some non-terminal to a word. And then it stops because you cannot expand the word to anything else. Okay, so that's a grammar. And that's pretty much all I'm going to tell you from automata theory. But I think you can be now pretty comfortable with these. And then there is this thing that we call a leftmost derivation, which is basically a way to start from S, which is the start symbol, and generate some sequence of words from the vocabulary, okay, which can be derived by this grammar. Okay, so basically the leftmost derivation is this sequence of strings, S1 to Sn, where we don't know what n is. Okay, and S1 basically is the start symbol, S. And then for each extra S, what you do is you take the first or the leftmost non-terminal, okay, in your string, and you replace it with something else according to the grammar until you get stuck. Okay, so this is an example, but so S, NP, VP, and then so, but let's see how we derive it. So we start with S, okay, and again recall this is our grammar, so these are the rules. Okay, so we start with S, and then we apply this rule, S rewrites to NP, VP, and we get this string. Now we look at the leftmost, which is NP, and we say, okay, NP can be adjective noun, so we have this. Okay, now the leftmost is adjective, and we kind of have, okay, so this can be fruit. Then noun translate to flies, then VP is VB and NP, and then like, and then determiner noun, and then and then banana, and then we get fruit flies like a banana. Okay, so that was a derivation where we derived this sentence from this symbol, okay, following the grammar rules. And there are many orders in which we can do this derivation. So we could have replaced here VP and not NP in the first round, and then do the NP after. But we want to kind of we want the thing to be unique, so we just say we will replace every time the leftmost one. So now we have one canonical derivation. Okay, so given S, you can derive very many sentences, which is nice. And people sometimes kind of ask, okay, given this grammar, what set of strings can it derive? Okay, and what can we say about them? But this is not our question. So our question is the opposite. It's basically, okay, I see this string that someone gave me, and I want to know what is the order of things that derived it, or can it even be derived from this grammar? Okay, and this derivation can be written as a tree, okay, and you can have many trees. So how can this be a tree? Basically, if you replace S with NP-VP, then there is S and then NP and VP below it, okay? Okay, and so we have this context-free grammar. Again, this is an example, and then you can derive this one. Okay, so again, we took S, we replaced it with NP and VP. Then we took NP and replaced it with adjective and noun, and then adjective with fruit, noun with flies, and so on. Okay, so this guy maps to this guy directly. And we can have like many other things that we can derive. Okay, some of them make sense more than others, but like they're all grammatical according to this thing. Okay, and again, as I said, the parsing problem is given this string, you want to recover the derivation. So what was the process that gave rise to the string, or what is the tree that is behind this string? So that's our problem here. And now let's talk about how you do parsing with what we call probabilistic context-free grammars, or PCFGs. So what we've seen until now is CFGs, context-free grammars, okay? And we'll see the P part in a minute. Okay, so parsing with PCFGs. So there are a few assumptions over here. So let's spell them out. So we assume that natural language is generated by a CFG. So there is some grammar that can generate all and only sentences in natural language. Okay? And we assume that we have this grammar. Okay? And under this assumption, then parsing is easy. Given a sentence, you just have to find some chain of derivation that starts from S and generates it. Okay? These assumptions are not quite easy to make, especially we have the grammar is hard. We don't quite have the grammar. Linguists keep debating on what the actual grammar is, but we do have many different grammars which are approximate. Okay? But let's also kind of take a closer look at these assumptions. So first, natural language is not generated by a CFG. Okay, so there are many kind of evidence given various different kind of somewhat esoteric constructions in different languages that kind of contradict like language theory and says that like if you can have like this structure, so something that occurs n times and sometimes n times and so on, then this cannot be represented by a CFG. And some languages do have these structures. So there are like many kind of arguments as to why language is not generated by a CFG or why CFG is not a good model of language. And that's a hard problem. But our solution is that we don't care. We assume very, very hard that it is generated by a CFG. So, OK, there are these facts that kind of contradict us. We just ignore them for now, and it will be good enough, we hope. Well, that's what we do, at least. OK? And the other problem is, OK, so we assume that, but we don't have the grammar. OK? Actually, finding this grammar is basically the main goal of many people in linguistics or syntacticians. So what is the grammar and what is the kind of mechanism behind it? Okay, but let's assume that we can ask some linguist to write a grammar for us, and it shouldn't be the grammar, it should be a grammar which is good enough, okay, which covers most of English or most of Italian or most of Portuguese or whatever. And then, of course, we have to find the chain of derivation, and it's also not very easy, okay? But this is actually easier because for this we actually have a solution. There is an algorithm that uses programming, and we'll see it in a minute. Okay, so so if we had a grammar, it would be much easier to find some derivation for the sentence based on this grammar than to actually get the grammar. Okay, and then of course there is this other problem that for a real grammar, like not this toy one that I showed you, for any sentence you can possibly find hundreds of different derivations for it. Okay, and most of them will be incorrect. And you don't want a derivation, you want the best derivation. Okay, so you need to find, or the correct one. So you need to define what best means somehow. And then you need this definition of best to correlate with correct, because it may not be the same thing. And you have to somehow search for the best one, not for just a one. Okay, and also for this we have a solution, and we'll see how you do that. Okay, so let's now talk about how you obtain the grammar. So as I said, we could ask some genius linguists to write it, but it's hard. There are many rules, there are many complex interactions, they are hard to describe. It's hard to find a genius linguist, and it's even more hard to find a linguist which is both a genius and wants to work for us on this silly tree problem, because the ones who are kind of geniuses don't care about mundane stuff like what is the grammar of English. They want to find generalizations or some other things that linguists care about. So they don't, as I said, the things that linguists agree on, they consider to be the boring stuff, and they don't want to work on the boring stuff and write our little grammars. They want to work on the hard stuff, which we don't care about. And if we find some less genius linguists, they may want to actually work on our kind of descriptions, but, well, they're not geniuses. So it's a hard problem to work on. Having said that, there are some linguists that kind of wrote very long books describing what is kind of how English looks like, and there are projects in which linguists write grammars for different languages. But this is not really scalable and not really maintainable, so we'll not use this approach, at least not in this talk today. Okay? And the easier way is that we can ask a linguist, or even not a linguist, but someone who learned how to do it for a while, to just grow trees. Okay? So asking someone, give me the grammar or give me the system behind this complex phenomena is hard to do. But if we can ask him, okay, here's a sentence, what is its structure? And here is some other sentence, what is its structure, okay? Then you don't have to be a genius for it, just need to know some rules and be able to map from string to trees. And that's much easier to do, okay? And then if we have a large set of trees, okay, we can basically extract the grammar from them. Okay, so we won't have the kind of good grammar for everything, but we will have a grammar that can derive all of these trees. Okay, how do we know that it can derive all of them? Well, because we took the rules from all of them. Okay, so for each of them, there is a set of rules that can derive it. Okay, and then the result of this process, where we ask someone to annotate trees, is called a tree bank. Okay, and it's not that easy to do, but it's not that hard. So for English, we have something called the English tree bank or the pen tree bank. It's 40K sentences, okay, that people manually annotated with tree structure. And then there are tree banks for many other languages, usually much smaller, like 5K, 10K sentences. But it usually is good enough to actually do something useful with them. So of course, larger is better, okay? But even with like 5K trees, you can do something quite reasonable and get a quite useful parser at least. Okay, so how does a tree bank look like? It's a file with many things that look like that. Okay, so this is a description of a tree in ASCII text with like brackets and so on. Okay, so a tree starts here and ends here. And the first thing is an S, and the S kind of expands to NP and VP. The NP extracts to NP and HP, and so on. Okay, so it takes some time to get used to reading it, but it's not very hard. So there is a very clear connection between trees and these like brackets. Okay. And then when we have this tree bank, we can do supervised learning. So we get this list of trees. We have some mechanism that extract knowledge from them. And then we have a semi-smart system that can be used to parse things or to kind of reverse the process. Okay, so how do we extract CFG rules from trees? This is actually very simple. So the leaves of the tree define our vocabulary, okay, sigma. The nodes of the tree define what our non-terminals are, okay? And each node and its children is a rule in our system. Okay, so if we have like this tree, okay, let's start taking out rules from it. So we can look at this top branch and say, okay, so that's a rule. S goes to NPVP. We've seen it once, so it's a valid rule. NP goes to alg noun, so that's an extra rule. Alg goes to fruit, that's also a rule, and so on. Okay, and we do this for many trees. Okay, and we get a large grammar. And we'll get some duplicates, which is good because it means that like the rules are reusable. And then we can just like count how many times we saw each rule. Okay, and then we have like a counted set of rules, which is our grammar. Okay, so now we know how to go from trees to a grammar, which is good enough for us. And now the next problem is that we need to somehow score these rules, okay, or score the trees. And here we say, okay, so let's assume that English is not generated from a CFG, but from a PCFG. So a PCFG is a probabilistic CFG, okay, and it doesn't add any more power to what can be derived, okay. So the same arguments before that that English is not a CFG applies also here. But what we do get from the PCFG is this extra power that gives us the ability to assign some score or some probability to each tree structure. Okay? And then if we can assign for each tree some kind of a probability, we can ask, okay, so what is the most probable one? Okay? What's the best one? And the way we do it is that basically each rule have with it some probability. And it is structured in a way that all of the probabilities of the same left-hand side sum to 1. Okay, so an NP can expand to either this or that or the other thing, and like they sum to 1 in their probability. Okay, and then if you multiply all of the probabilities in a derivation, gives you the probability of the tree itself. Okay, and then we want a tree with the max probability. Should I not move? Okay. Okay, so we want a tree with the max probability. And so this fact is not trivial. It should be proved, and like there is some proof. But let's assume that it is trivial, and I think it's kind of convincing enough also if you don't prove it. It makes sense. Okay? So more formally, the probability of the tree and the sentence is you look at all the rules in this derivation, okay, of this tree. Okay, so all of the rules in the tree, and you have some probability with each rule, and you multiply all of them, and then you get the probability of this tree over this sentence. And then parsing, okay, or your tree, is you want to maximize, okay, over all of the possible trees in the sentence, you want the most probable tree given the sentence, which is proportional to the most probable tree-sentence pair, which is what we have here. Okay? So we look over all of the trees, we maximize this quantity, and then we get our best tree. So that's parsing. And actually, it's just like a form of structural prediction. Okay, so we say that you kind of multiply all of these probabilities. You can also think of this as the sum of the log of all of them. Okay, they go in the same direction. Okay, and you can also, okay, so that's the log of the probability. But you can also think that so we have a score for each rule. Okay, and we want to maximize that. Okay, so this is also equivalent. Okay, and basically what we have here is we decompose our tree into rules. Okay, so we need to assign a score to a tree, but that's hard. So we assign score to rules, and each rule has its own local score. Okay, and we want to find a tree that will maximize, that has the best rule in it, and that they actually work well together, because otherwise we cannot have them. Okay, so that's basically a case of what you've seen yesterday. Okay, and then the question is like, okay, so how do we learn these scores? And here we just learn them by something like which is probabilistic, but there are also other ways to score these parts of the tree. Okay, the rules. Okay, so let's see an example of a PCFG. So that's a very simple one. Okay, so we have S goes to NPVP, and that's the only S rule. So it has like a 1 probability. Okay, then NP can go to either adjnoun or detnoun, and so these sum to 1. Okay, and it's usually goes to determiner and sometimes to adjective. Okay, again VP there is only 1, so it's 1 probability. Adjective can go either fruit or angry. And fruit is less likely. Noun can be either flies or banana or tomato, and so on. Okay, and you have to distribute the probability between them. And usually, again, there are like many more items here. So these numbers are much smaller. Okay, but that's kind of the idea. And then if you do that, then for this tree, it's like probability under this grammar. Why? Because, okay, so S goes to NPVP, that's 1 over here. Then we look at NP goes to adjnoun, that's the 0.3. Adj goes to fruit, that's the 0.2, and so on. Okay, so that's how we can calculate for each part its score, and we multiply them, and we get the score of the tree. Okay. Now, parsing with PCFG is finding the most probable derivation for a sentence, and this can be done quite efficiently with an algorithm which is called the CKY algorithm, which will be the topic of the next few, I don't know, like 15 minutes, half an hour or so. Okay, so let's describe this algorithm. But before that, let's talk about how you obtain the actual rule probabilities. Okay, so there are many ways to learn them. The most common one is to estimate them from a tree bank. So we say that the probability of left-hand side goes to right-hand side, so like S goes to NPVP, okay, is the number of times that we've seen this rule divided by the number of times that we've seen this left-hand side go to anything. Okay, so it's a very basic estimate like you've seen in HMMs, basically. And we can also add smoothing and back off as before. Okay, if we have unknown words, like in the HMM, we can have these back off features. And there are also more elaborate ways to estimate that, but that's the most canonical, and let's say that we use that. Okay, so this is how we find the rules. And now the probabilities, but now let's talk about the actual algorithm, CKY, and how if you have a grammar and for each rule you have it's a score, how do you find the best tree? So so to kind of describe our problem more formally, our input is a sentence and a CFG, okay, with like weights on the rules. And let's say that n is the sentence length and g is the number of non-terminal symbols, okay? And if g is the number of non-terminal symbols, then we have O of g to the 3 rules, because each rule can have 3 symbols in it, okay? And the output is a parse tree, or the best part trees. Of course, we have many trees to go over, so the solution is to use blank programming. Okay, so like in Viterbi, that you have to kind of find the best path, you have to find the best tree. Okay, so CKY is called after the people who discovered it, Koch, Kasami, and Younger. They did it in kind of quite a while ago, and they did it independently. So it's not like one paper by all of them, but like this guy did it in 1960 something and didn't even publish. He just say, okay, yeah, we know that, and kind of it was known that it's something that he did. Then in 65, this guy did it, and in 67, this guy did it, okay? And it's somehow named after all of them, which is nice. I don't think it will happen today, but that's a piece of history. Okay, and it can solve 3 different problems. Okay, so actually when we talk about parsing, we can talk about how to do recognition, parsing, or disambiguation. So what's recognition is, can this string be generated by the grammar? So is there any derivation that will produce this string? Parsing just says, give me some possible derivation. I don't care which one. Okay, and disambiguation is, give me the best one. Okay, and CKY can do all of these in polynomial time. And we'll start by tackling this guy, which is a bit simpler to kind of describe, but it will be quite easy to extend it to also those 2 cases. Okay, so CKY can do all of these, but for any what we call a CNF grammar. Okay, so what's a CNF grammar? So CNF, something it's an abbreviation for Chomsky normal form. Okay, and it basically means that you want our grammar to be binary. Okay, so we basically need the left-hand side to be a single symbol, like we've seen, and we need the right-hand side to be either 2 non-terminals or 1 terminal. Okay, so that's all we allow. And you can easily extend it to also work with like unary rules. So A goes to B without C, okay, but not more than that. Okay, so this looks like a restriction, but it's really not. So it's easy to show, and we'll see it now, that any CFG can be converted to a CNF form. So we just do this. Okay. The downside is that it may expand the grammar to make it larger, but still very possible. Okay. So for like NL grammars, so we already have that each non-lexical, so each like part of speech goes to a word. So that's we have. And if we had like one thing going to 2 words, it's also easy to handle. Rules are okay. So the only problem is that is like these rules where we have like left-hand side and then a very long right-hand side, and we need it to be like length 2. Okay, so what do? It's called binarization. So we take a rule like that and we convert it into 3 different rules. Okay, which basically capture all of the information here. So so now S goes to NP, which is the kind of first thing. and this guy, which says I've seen an NP and I still have this to go. Okay? And now we have this extra symbol, which goes to this guy, and that's kind of deterministic. It goes to PP, which is the next one, and still have this to go. Okay, so we've seen this and we have this to go. Okay, and here we have this guy, which should be, no, it's the wrong one. It should be this guy that maps to VP and that. Okay, so basically so this guy kind of has the same probability as this one, and those one have one probability because that's the only way to expand them. Okay, so that's the process, and it's easy to do. Okay, so now finally, let's talk about CKY. So we have a grammar which we got from trees. We somehow managed to convert it to a CNF form. Now let's see how we can do this task that's saying, can we find a derivation from it? Or like, is there a derivation for this grammar, for this sentence? Okay, so the idea is to build the tree from bottom up. Okay, and we combine small units into larger ones, okay, using grammar rules. And when we left with only a single large tree, we just need to see that we can get S out of it. Okay, so there are many different trees, and we search over all of them, okay, using a program where we kind of share structure of smaller trees. Okay, so the idea is that if we know that there is some span from I to j, which is, say, an NP, and there is a span from j plus 1 to k, which is a VP, and we have this rule, S goes to NP VP, then we can derive a larger span, okay, from I to k, which is S. Okay, so let's draw this. So we have two subtrees, and we don't care like what the kind of what happens here or here inside, but we know that this span can be an NP and this span can be a VP, okay? And so we can combine them using this rule to get this tree, okay? And now we forgot what's in the inside. We only know that S can go to this longer thing. Okay, so that's the idea, and we can do it like that. So we have this guy and this guy and that guy, and together they are combined into the larger one. Okay. So that's the idea of like why it can work. By the way, if you want to add probabilities here, then if you know that this can be an NP with like some probability, and this can be a VP with some probability, then you just have to multiply this by this probability to get this guy's probability. Okay, so that's the recursion over here. Okay, so how do we do it in the algorithm? So there is this structure, which is half an array, okay, which we put on the side. Okay, and then we have the words over here, and basically each cell, okay, this or this or this or that, basically says it will contain all of the non-terminals that can derive some subsequence. Okay, so like for this cell, we are looking at this sequence, su, so, here. Okay, and this will contain all of the non-terminals that can derive su, so, here. Okay, and like for this guy, we have here girl. For this guy, we have girl with a telescope. Okay, so a span. And you can imagine each cell as an array with g dimensions, where g is the number of non-terminals. Okay, so for example, for this guy, okay, so her girl will have this table here with all of the non-terminals, and it cannot be an S, it cannot be an NP, it can be a VP, okay, it cannot be a PP, and so on. Okay, so we have to compute for each cell, okay, what it can be and what it cannot be. Okay, and we basically do it incrementally. Okay, so how do we do it? Basically, if we know what this can be, and we know what this can be, okay, then we have to somehow combine them using our rules, and then we know what this can be. Okay. So let's say that we kind of start with this cell. How do we fill it? So we just basically look at the word, and we say, okay, so what can derive this word? And we see that it could be a noun or a verb. Okay, so we can either sue someone, or sue is the name of a person. Okay, and you can do it also for all of the others. Basically, for each one, you do this lookup and you see which rules can derive this word. Okay, now here like one up. Okay, so basically you look what can this be and what can this be. Okay, and what rules do I have and how can I combine them? And then you can fill up this table, okay, which is also kind of pretty simple. Now, yeah, so this kind of looks at this and that and combines them. Now, if you're here, okay, it's a bit trickier, okay, because here you can combine either this cell and that cell, so either Sue and so her, okay, or Sue, so, and her, okay. And then if you go one up, it's the kind of same logic. It can either be like this single one and this tree length thing, or it can be like 2 and 2, okay, or it can be 3 and 1. Okay, so basically you look at all of the kind of things that are kind of smaller than it and below it, and see how you can combine them together. Okay, for this guy, it's kind of similar, so either this or and the 3, this, and so on. Okay, so that's the logic. Okay, now the question is like, okay, so now so I know how to fill each of these. Okay, and now in which order do I do it? So the key point is that when we handle one cell, we need all of its potential parts to be complete. Okay, so if we want to kind of fill this cell, or like this cell, then we said that we have to compare this and that, and this and that, and this and that, and that, okay? So when we fill it, we need all of those components to be there already, because we look at these tables and say, okay, what's in them, okay? So we just need an order that will do this. So like one possible order is to do this guy first, and then that guy, and then like all of these, because they are independent. And now just like go one row up and do this guy, which kind of depends on these two, and then this guy, and then like all of this row. Okay, and then we can go up one, and then like these are things. So when we do this, everything below it is already done. So like these two diagonals are done. When we do this, then like these two are done, and so on. So we can just like go in this like row by row by row by row by row. Okay, and then we get to the top. And when we are at the top, we just need to verify, is there an S there? Okay, can an S kind of have the whole thing? And if there is an S there, then we are done. Okay, and we can find a derivation. So that's one order. We can also do it like that. So we can go like this. So we do this, and then we do this, and then we do that, and then we do this, and then we do this, and we do that, and so on. So this is also a good order to do things. It doesn't really matter which one you use. This one is called the left corner parsing, because it goes for the corner and up. And the nice thing about this one is that it adds the words like one at a time, okay, and not like gradually. So if you want to do like a setup where you get the words one after the other, then this can be useful for you as an order. Okay, so that's the algorithm, and I did not give you the code for it, but it's very easy to find online, and it's very easy to maybe kind of infer it from the thing. You just have to have like 3 loops. One of them goes over all of the cells, or like so 2 of them go over the cells, so like rows and columns, and then for each cell you go over all of the possible subparts that can connect it, and for all of the non-terminals. Okay, so what's the complexity? So we have to fill n squared times g cells, okay, because so the matrix is n by n, so it's n2, and each one of them has g symbols in it, so we have to fill all of that. And there are g to the 12 times n to fill each one of them. Why? Because so g to the second is based on the grammar, okay? We can combine 2 things to derive some other thing. And there are n ways to fill each one, because like this guy can be either 1 or this or this or that. Okay, so that's the other n there. So in total, it's g to the third and n to the third. So that's basically depends on the sentence, and that's on the grammar. Okay, so that's called the grammar constant. And for larger grammars, it's slower to parse, and there are tricks to go over it, but we will not go into them. Okay, so up until now, we just told you how to see if we can derive something, but not what the parse is. But actually, the extension to actual parsing is quite easy. We just have to, for each cell, find or keep track of how we derived it. So when we say, okay, so this guy can be a VP, okay, we just have to remember, and we know that this can be a VP because we combined this guy and that guy, okay. And if we know that, then so we kind of have this tree part that combine it. So we have to kind of keep track of what we combined to know this, and then we can find the actual tree. And if we want to have the best tree, then again, it's kind of easy to extend for each non-terminal. So for each one of these kind of NP there, we not only keep this can be an NP, but this can be an NP with like probabilities of 0.09, okay, or some other number. And then we just have to take the max over those. Okay, so it's kind of like Viterbi, and I'm not going into the actual details here, but it's easy to fill out if you look to that. But again, I doubt that many of you will actually go and do this. And if you do, then it really is a good exercise to do it yourselves, okay, to kind of figure it out. Okay, so I will not spell it out, but that's how it works. Okay, so to recap this part, you extract the grammar and the probabilities from a tree bank. So the first step is actually to create this tree bank, okay? But we can assume that this is given because people did that already, okay? And then you have the grammar and the probabilities, and then given a sentence, you use CQI to recover the highest scoring tree, okay, under this grammar. Okay, so that's the parsing algorithm, and it doesn't really work. Okay, so what do I mean by it doesn't really work? So it is correct. It will recover the best tree according to the grammar, okay, or the one with the highest score. But the problem is that these best trees are quite bad. Bad in the sense that they don't match the gold trees or what we want them to be. Okay? Why? Because it's not a very strong or good model. So we find the best tree, but the best tree is not the correct tree. Okay? Why? Because our definition of best was not the right one. We just like say, okay, we have these probabilities, let's multiply them, and let's see what happens. Okay, and if you do it, then you get a parsing score of 73, and these days we would like to get to like 90s or something like that. Okay, and we can get to like 90. And let's see how we close this gap. Okay, so let's see what is the problem. Yes.
But the 73 is the iPhone score. It's upon the 73 again. That is pretty high, right? That's a classification and stuff.
Okay, so yeah, I did not describe how you actually score trees, and then I don't know the name, but he asked, this looks pretty high. So I want to stress that this does not mean that for each sentence we are either wrong or right, and we are right 70% of the time. Okay, it means that it's 73 F-score over parts of the tree. So if we kind of if we think of a tree as like nested spans, okay, then we can get 70% of the spans correctly. Okay, so either each of our trees is only correct in like 3/4 of the time of its structure, or we have some trees that are very good and some that are very bad. Okay, in practice, this does like very low if you actually measure like how many are kind of good entirely. Okay, so it scores only part of the trees, and that's the kind of metric that we use. Of course, if you do 100 here, it's like good overall, but this is pretty low. But you are right that like if we go to like 80 something, it's already much better. Okay, and it's actually very useful already, and like 90 is actually very good. Okay, and also you're right that like what the metric that we use to measure things is very, very important. But I don't have time today to talk about it, so we'll not talk about the metrics, but they are important, of course. Okay, so some limitations of the PCFG model that we have seen. So one limitation that it's not sensitive to words. Okay, it has very little connection between the actual words and the structure. We'll see that. And it's also not very sensitive to how the overall structure looks like. Okay, so what does it mean? And these are some trees from Mike Collins. So here we have two trees. Workers dumped sacks into a bin, and workers dumped sacks into a bin with a wrong analysis. Okay, so so this guy into a bin connects either to sacks or to dumped sacks. Okay, so it's like different structures, and one of them is good, the other is bad. And if you look at the rules in each of these, you see that the only difference between these rules and those rules is this single rule. So either VP goes to VPPP or NP goes to NPPP. Okay, so that's the only difference. And the decision, if you want to kind of attach like this or like that, only depends on what this rule scores. Okay, so every time it sees this kind of decision, it will choose one of them, and it will choose them the same one each time because it's kind of deterministic, because either this or that has a higher score all the time. Okay, and this decision does not care about the actual words. Okay, so you will decide one way or the other based on the score of these rules and not the words, which is bad because here you need the words to kind of know what's right or wrong. Okay, even worse, you have here this thing, dogs in houses and cats. Okay, or dogs in houses and cats. Okay, one is wrong, one is correct. Okay, again, the words may help you to understand what's correct or not. And these two parsers have the exact same rules. Okay, so no matter how you assign the scores to the rules, you cannot distinguish between these. Okay, because they have the same score under whatever thing you try, because these are the rules. Okay, so that's a problem. Okay, we cannot really use the words to disambiguate. And then the other problem, it's this thing that we call structural preferences. So there are trees that are more likely than others without even thinking about the words. Okay, so you have this structure and this one. Okay, and again, these two have the same rules. Okay, so you can't really tell them apart. But we do know that this one is much more likely than that one. Why? Because trees in general tend to have this chain-like structure and not this one. So we kind of prefer to kind of attach things close together and not farther apart. Okay, but the PCFG cannot actually model this because it will not distinguish them. Okay, so there are things about trees that we know that are not modeled in the CFG. Okay, so let's see how we tackle these problems to improve. And the first idea is something that's called Lexicalized PCFG. Okay, and this kind of tackles the problem of not caring about the words. Okay, so the idea is to make the PCFG aware of the words. Okay, and it's called a lexicalized PCFG, which means so lexicalized is with words. Okay, so it's a PCFG with words, and the main idea is something that's called head words. Okay, so what's a head word? So each constituent or each sub sentence, each subtree basically has one word which captures its essence. Okay, so let's see here. So the S, the sentence, John saw the young boy with the large hat. So what is the main word over here? So it could be John. It's not John usually, but I mean, we don't find it to be John. We say that saw is the main thing because that's kind of the action. Okay, so saw is the kind of main word here, and then John and the young boy with the large hat are kind of its arguments. Okay, so that's the main word here. Now we can look at the VP saw, the young boy with the large hat, and again here the head word is saw. Okay. The young boy with the large hat, now the main word is boy. Okay? The large hat, well, hat, okay? With the large hat, okay, now we don't, it's a bit tricky. It can be either hat or wheat, okay? So it can be it can be hat. And now we need to decide somehow, like because both of them are valid. And hat is what we call the semantic head, which is where the semantics is, like the main content. And wheat is what we call the functional head, which is basically what is the role of this thing. Okay, so this is kind of attaches as a preposition phrase, so wheat is a kind of main preposition. So we need to choose, and usually it's common to go with wheat as the kind of head of this, with the functional one. Okay, but the main point here is that for each phrase we can define one word which is the main word of this phrase. Okay. And like the main word, in a sense, can replace this phrase. So if you are saying, okay, what is this about? So this is about seeing. What is this about? About seeing. What is this about? This is about a boy. Okay, that's about a hat, and that's with something. That's something that we do with something. Okay. Okay, and then we can also add this to our grammar. We can say if we have an S go to an NP and a VP, then the VP will be the head of this guy. Okay, so the head of the S comes from the head of the VP. Okay, and the head of a VP comes from the verb. Okay, and so on. So this is a core idea in syntax or in linguistics, which we also use here. Okay. And basically, the idea is that like this head word kind of represents the phrase in a very concise manner, but like it's the main content of this thing. Okay, so and then we can like basically add words to the trees. Okay, so here you have this tree. The lawyer questioned the witness. Okay, and we can say, okay, so there is the head, witness has witness as the head, and NP has witness as the head. Question is the head, lawyer, question, and so on. Okay, so basically, for each sub-tree, we say what the head word is. Okay, and the head word comes from somewhere below. Okay, so now we have non-terminals that have heads on them. Okay, and also one property here is the head word also always comes from like one of the children. Okay, so questions come from this side, witness from that side. Okay, but we always choose one side, and that's the head of the larger thing. Okay, so we kind of do this up propagation of the heads. Okay, so that's the so now our trees look like that. We have a non-terminal symbol and some word on each one. Okay. Now, if you have seen like our grammar from before, where we have rules that look like x goes to y1, y2, okay? Now what we have is x and a head word goes to y and a head word and some other word, or x and a head word goes to y and some word and y as with the head word. Okay, so basically we added words to our grammar rules. This may be confusing. This is how it looks. Okay, so S saw, okay, goes to NP man and VP saw. Okay, and the head comes from the second one. Okay, VP saw goes to VT saw and NP dog, and this comes from the first one, and so on. Okay, so now we have a much larger grammar. Okay, but it's still a grammar, and we can parse with it. Of course, now it's hard because first we have much more sparsity, because if we can kind of count reliably S goes to NP VP, because we can see it many times, it's much harder to count S saw go to NP man VP saw, because this happens much less often. Okay, but let's assume that we have good smoothing and we can do that. Still, we have this problem that now we have a huge grammar. Okay. So if, like previously, we had maybe like 50 symbols in our grammar, so we have like 50 cubed different number of possible rules. Now we have like a huge vocabulary, okay, and we have a much larger grammar. Okay, so we have like g cubed, or like a number of term symbol cubed, and this squared, because for each rule we have 2 words. Okay, so that's huge. And we can parse it like in this time, right? Because we just like have a now larger grammar. But again, this guy is huge because like so this is all the world. So it's like 100,000 something, or like 30,000. It's very, very large. But what we can do is, okay, we can say, but for a given sentence, we don't have all the words. We only have n words of the sentence. Okay, so it can be only one of those. It cannot be like everything. So we can parse slightly faster. Okay, we can parse in like n to the 5th time. Okay, with the previous grammar. Okay, so it's heavy, but it's manageable. Okay, for those of you who did not follow the argument and care about it, talk to me later, and I will explain. But let's just kind of get it now for granted or for given that we can parse with n to the 5th time with these kind of grammars. Okay, and when we do that, we get much higher score. So the first systems that did this went to like 84, then to like 86, 87, and 89 was kind of the best one. So it's get much better accuracies. So that's one trick, but it's not the only thing that we can do. And now we'll see some other method that does it without lexicalization, or like an alternative to this. Okay, and this basically tries to capture the lack of like sensitivity to structure. So this problem is also solved by adding the head words, and maybe it's actually the main thing that's solved by the head words. But we can also do maybe without adding words to the grammar. Okay, because adding words is kind of expensive and kind of brute force. Okay, let's do something kind of more subtle. So now, and that's very nice work from Kahn and Manning from 2003, I think, where they showed that what you can do without like words at all. And the idea here is, okay, so if you look at the CFG or the PCFG, its main assumption is that if you know like NP and VP, then you for knowing S, you don't care about like what is the connection between NP and VP or what's inside here. Okay, so you just so there is some NP with some kind of things below it, and like some VP and like things below it, but there is no shared information between those, and basically this and that are independent given this S. Okay. So basically everything that kind of needs to follow from from here to there has to pass through this NP. So if we know that it's an NP here, it will influence S and the VP, okay? But that's it. So like everything that kind of describes this tree is kind of boils down to this NP, okay? And this may be a bit too strong. Okay, so let's so let's see what happens. So basically, if we have like the word question, okay, then it affects V, and that's it. Okay, so the tree here is kind of does not care about question if we know it's a V. Okay, but if we have like the words over here, okay, then question affects V, but also these two because it's the head. Okay, so now this word affects all of those, which is much larger. Okay, so when we add these words to the grammar, we now make it much more expressive in terms of like what it can cover, or it makes a much less naive assumption. Okay, and even without words, we can see that there are like something that we should consider. So, for example, if you look at the way we kind of expand NPs, okay, so what can an NP expand to? Okay, so if you look at all of the NPs, then it could be either NPPP with like 11% probability, or DTNN with 9, or PRP with 6. So that's for all NPs. But if you look at only NPs under S, okay, so it said that S goes to NPVP, right? So like only these NPs, then they are very likely to be like a pronoun and these are less likely. Okay, and if you look at NPs under VP, then now this is likely and these are less likely. Okay, so if you know what is the parent of this NP, okay, then you can influence much better which rule is chosen. Okay, so you need to know the structure. So some intuition on like why this happens. So pronoun is like words like he, I, she, and so on. Okay, her maybe, and it's much more likely to say I something, like I went, I ate, I something, than something and a pronoun. Okay, so it is much more likely to say I saw something than saw him or her. So it also happens, but less frequently. Okay. So the idea here, and that's also very, very briefly, the idea is that you can take the tree and add some annotation on those terminals to kind of give you more information about this subtree. Okay. So for example, here we say for each non-terminal, okay, for each symbol, we also add its parent. Okay, so here it's not add-p, it's add-p under VP. Okay, and that's not VP, it's VP under S, and NP under S, and S under root. Okay, so for each symbol in the tree, we just like add its parent as a concatenation, and now we have much more elaborate symbols that are more kind of attuned to where they are, like with the rest. So it's still independent of the others, but less so. Okay, and some other thing we can do. Okay, so that's an NP that has a pause below it. Okay, so like this caret here, that kind of thing here marks that's the parent, and this marks that something is below me. So that's kind of an NP that has something below it. Okay, and then when we kind of look at this guy, it says, okay, so this may be more likely here than something else. And then so they went over this and did kind of, they thought quite a bit and kind of tried things. And then they came up with like many different annotation. And now their trees look like that. Okay, so that's not only a VBZ, but it's a VBZ which is a B form and under a VP. And that's VP under S with the kind of bare infinitive and so on. Kind of marked the trees. And then if you parse with that, you get to 86 already, which is most of the thing that we kind of got from the words we get from this. So the key point here is that it really depends. So when you break your tree apart into rules, okay, it really kind of is important how these rules look like, and you need to think about it at some point and maybe have better trees or better rules. Okay. And that idea basically said, okay, so we take a symbol like VBZ and we kind of have it like split. So now we have one VBZ, or like we take this NP, and now we have NP SB and we have NP VPB. Okay, so like two different kinds of NPs, okay, which we manually found. Okay, and now the actual best parser until very, very recently worked in a way that say, okay, so let's find these splits automatically, and that's work primarily by Slav Petrov and also Dan Klein. And what they said is, okay, so let's take these trees that like look like that and try to kind of split these symbols. So now we have NP0 and NP1, and we'll have maybe VP0 and VP1 and VP2 and VP3 and so on. We basically split each symbol into several ones. And we have this clever mechanism to, for each tree, find the best split such that everything together will have the best probability. And that's hand waving. I don't go into the details, but the idea is to kind of find these splits in an automatic manner. Okay? And if you do that, then now you have a grammar that has these like special rules. Okay, where each symbol is like split into several different symbols. Okay, and so this grammar is kind of several times larger than the original one. But if you parse with it, you get a much higher accuracy, like around 90s. okay, because it captures the data very, very well. Okay, so that's the main idea, and it actually works. It's a very nice paper by Slav Petrov, and you should look it up if you care about this. It's kind of it's a cool trick. Okay. So, and of course, at the end, after you parse, you are left with trees that look like S0 goes to NP1, VP5, whatever. You just delete all of those numbers and get what you care about, which is just the S and NP and the VP. Okay, so to summarize this half part of the talk, which is right on time, yes. We decompose a tree into parts, which are the grammar rules. We assign a score to each rule. Okay, and these rules can be either just from the trees or from trees with some annotation or with trees with some like splitting. Okay, but we have a score for each rule. And then we find the best scoring tree using CKY. And maybe we do some tricks for somehow better scoring of the rules, which I did not really talk about. But you can think about smoothing techniques, and you can think about maybe more kind of learning like you've seen yesterday. We want to find scores that will maximize the right tree and so on, and with features, and people also do that. Okay, so that's how you parse for phrase-based trees. After the break, we'll talk about dependency parsing, which is like dependency trees. Let's finish at this point. The half of this tutorial. Okay, and in the last half, we talked about phrase-based parsing, or how we can produce these trees that have this nesting structure of like larger and larger units, VPs and NPs, and so on. And we talked about PCFGs. And now we'll move into dependency parsing, which is a different kind of structure that we want to recover. But it also relates quite closely to the previous approach. Okay, so yeah. Okay, so let's start by talking about what is this dependency that we are trying to recover. And our story here begins with the concept of head words. Okay, so if you recall, like half an hour ago or so, we talked, maybe an hour ago, so you may have forgotten already, but we talked about head words, okay, which basically means that every phrase, every subpart of the sentence, okay, has the main word that is the kind of head of this part. And you can see that you can add head words to parse trees like that. Okay, so basically we annotate each non-terminal with some head that will capture the main thing from the tree below it. Okay, so here you have the word questioned, and it kind of captures this VP over here. And here you have also the word questioned, and it kind of captures this S over here. And below question, there is lawyer and there is question. Okay, so now we basically have a tree with words in it. And basically what happens here, or what people realize, is that, okay, so we have this guy that kind of defines some hierarchy between phrases and say, okay, this thing is a VP, this thing is an NP, and so on. But maybe we don't really care about this so much. And then we have this thing which is words. It's going to basically add words to this. But what if we only cared about relations between words? So we want to know that there is some kind of relation between questions and lawyer or question and witness, okay, but not the kind of entire structure or like the nesting around it. And the idea is that if we take the trees with the head annotations and we forget about the non-terminals, okay, all of these phrases or constituents, then we get what is called a dependency structure, okay, which is some form of representation that captures the relation between words in a sentence. Okay, so we start with this kind of tree with head annotations, okay, and then we basically remove all of those NP, VP, VT, NP, and so on, and we are left with this guy, okay, which is basically all of the words that were there. And now we can look at basically chains of things which are the same word. Okay, so these are all the same, this is all the same, all the same. And we basically remove all of the chain until its top. And then we are left with this guy. Okay? So if we kind of delete this, okay, so now witness is under, we delete all of the red ones. So question, lawyer, okay? So we basically remove all of those red things, okay? And then we are left with this, okay? And this tells you that the main word is question. Question is the head word of the entire thing, and it has two modifiers. It has lawyer and witness as its modifiers, okay? And lawyer has one modifier there, and witness has one which is also there, okay? So that's basically dependencies between words, okay? So very much related to the previous thing, but we focus only on the words. And it can also be drawn like that, okay? So you may have seen this and not this representation, but they are the same, okay? So if you take this one and you take the word question, you kind of pull it up and let those things drop below it, you will achieve this. Okay, so it's the very same thing, but here the kind of direction is implied by the height. So question is above witness. Okay, and here it's implied by the arrow direction. So question is the head of witness. Okay, and some of you may have seen things like that where the arrows are the other way around. Okay, and like some faces here like do this notion that kind of implies this, and that's fine. Like people kind of keep arguing on how to draw the arrows, like which is the head and which is the modifier. I use this notation, but it's not really important. So the main thing here is that we have words. Each word is the head of some other words, and basically each word has one parent, which is its head. Okay, so each word has a single parent. We have a tree. And one of the words, here it's the word question, doesn't have a parent, or you can say its parent is the root or the main word of the sentence. Okay? And why is this useful? Because if you have this, you can say, okay, who is the parent of this word? Okay? Or who are the children of this word? Or what's the main word of the sentence? Okay, so the main word is question, and it has two children, witness and lawyer, okay, which is kind of important to know. It's kind of hard to work with these right now because we don't know what is the kind of relation between question and lawyer or question and witness. But okay, let's get to it in a minute. And usually like things are even longer, so you have like this structure. Okay, so it's still nested and so on, but you can have like larger things. And here again, it's really, so here the main word is heard, and then questioned, and then like lawyer and so on. Okay, so heard, I, and questioned. Okay, so I heard that something about questioning happened. Okay, what happened? It's something that involved a lawyer and witness, and it was under oath and it was yesterday. Okay, so you can kind of infer these things. It's kind of hard to infer them though because we don't know what each of these arrows represent. So usually people add labels on these things. Okay, so it's not just a relation between words, it's a relation with labels on it. Okay, so like questioned is the causal complement of heard, and I is the subject of heard, and so on. Okay, and these roles are syntactic, so they mean what is the grammatical function that this word plays with respect to the other one. It's not semantic, it doesn't give you the actual meaning of like what happened. But some things like subject or object are sort of also imply who are the participants of this thing. It doesn't give you real semantics, but it's close enough that you can actually work with it to do something useful. So if you know what these roles are, you can actually kind of ask things about them, or like what are likely subjects of some verb, right? And you can kind of count that, or what verbs go with this subject. So like basically, what does this thing do? So usually the subject is the one that does things, and like in the verb, not always, but usually. So that's kind of useful. Now you may ask, okay, but how do you know these labels? Okay, so if you create trees automatically, manually, so like someone annotates the tree and goes, okay, so I think this word relates to this one, then you can also say, okay, and I think the label is that. Okay, so people kind of annotate this from scratch, and it's good. If you are converting from a phrase-based tree, okay, so basically you went like from this to that, right? And now you don't have labels, but you can also add labels automatically based on how this tree looked. Okay, so and you can write some heuristic rules that say if we had this S, NP, VP structure, then this NP is the subject, so this head is the subject, and so on. Okay, so you can infer these relations. Well, you cannot usually, like most of you, but like some of you can, and some other people can infer these relations from the kind of tree structure. Okay, so we want to parse into this. Okay, so we want to have a sentence and produce this kind of form. Okay, so that's our main question. How do we do this? And actually, we don't really parse from this. We parse from this and the POS tags that we kind of also inferred, and try to build some tree on top of that. Okay, and I will be talking about trees without labels throughout this talk, but the labels are easy to add to any algorithm that is unlabeled by just instead of having to say what is the best connection, it's what's the best connection and the best label, but that's kind of very easy to add into every framework that you are working with. Okay. Now, another thing to say about trees is this distinction between projective trees and non-projective trees. Okay, so trees which are projective are well nested. Okay, basically no crossing arcs, so you can draw them on a plane. Okay, and everything is above the sentence, and nothing crosses. Okay, so that's called a projective tree, and it's very common. Most trees in English are projective, and it's also the case in many other languages that they are projective. That's kind of a property of language. Also, if your trees came from this process, then they must be projective. There is no other way for them to be non-projective, unless there are empty elements in this tree, which I did not discuss at all, but it's something that syntax has, and then it might be non-projective. But if you do your annotation from scratch, then you may get some non-projective relations, okay, or some crossing arcs. So here we see an English sentence, John saw a dog yesterday, which was a Yorkshire Terrier, which is a bit kind of not very natural, but is definitely possible in English. And here we have this kind of crossing arc between saw yesterday and dog was. Okay, so that's kind of a structure which is non-projective. And so these things can happen. It's kind of rare in English. It's much more common in some other languages, like in Czech, it's very common, for example. And there is this kind of spectrum of common or not. And why am I telling you that? Because the parsing algorithms for this or for that are different. So if you want to basically search over all of the possible trees, okay, that are projective, then it is maybe slightly harder problem than to search over all trees, and that you don't care if they are projective or not. But maybe you can also use this thing that are projective to kind of make it easier. And also, if you know that your language, like English, is mostly projective, you may want to say, okay, so I want to find the best one of these and not one of these, because it will kind of constrain my space and kind of prune away all of the things that I kind of believe a priori that are less likely. So it's kind of maybe better to do. And if you allow also these structures, then you kind of may get many invalid ones that are just not very good. So you may want to constrain. But if your language is non-projective, like Czech, you actually want to do this because otherwise you will lose many things. Okay, so most parsing algorithms work traditionally with these trees, which are projective. And there is also some research on how to do these in a good way. So these are slightly more complex to do in some cases. But there is also work on that. Okay, so just be aware of this distinction. And people in parsing talk a lot about projectivity. So that's this thing. Do you have crossing arcs or not? Okay. And now just before we move into parsing, we just say that dependency representation is not a single thing. Okay, so there are many different ways to have dependencies over a sentence, okay? So basically, if you choose different kind of heads, let's say we talked about functional and like semantic heads. So with a large hat could be either with or hat can be the head, okay? So this happens quite often in many cases, okay? That he saw yesterday, so either so or that is the head, and you have to decide, okay, which of them, and you do it consistently. But every kind of group of people can define what it kind of rather put the kind of stress on and choose either this or that, okay? And this will kind of give you different trees, okay? Also, people kind of may argue on like what are the labels that you want to. So even if we know what will attach to what, maybe the label names will be a bit different, okay? And usually each language has its own tree bank with its own choices. Okay, so it's not really the same structure, and also within a language, often there are like 3 tree banks, each one of them with a different choice because it was done by different groups, and these groups really don't want to talk to each other, or like they hate each other, and they kind of each one believes that its own choice is the right true one, and like the others are doing crap. So it's really hard to kind of use these things together. Although it's interesting thing to try and work with. And then we have this new project, or not so new anymore, but like it's running for several years, which is called universal dependencies. And the idea here, so it's a project that spans many different institutions in many different countries, okay? And the idea is that we want to produce a set of annotation which is consistent across languages. So we say, okay, so maybe we disagree on what the kind of head is or the label is, but let's put these things aside and like let's define some canonical thing that we always choose the head to be this or that, and we always use these labels, okay? And it may not capture all of the kind of things in all of the languages, but it tries to do a good way of kind of capturing 98% of all of the languages, okay? Accurately, and the rest will do somehow, okay? And people kind of agree on this, and then kind of have tree banks in the same representation, okay? And this has been going on for a while now, and there are like I think 50 languages now, or something like that, maybe even more, with like varying sizes, but they are all under the same annotation, which is very, very nice. It does allow some specialization, so there is a core label set, so like they all have like subjects and objects and so on, but some may be like specialized. So you can say for this language there is like a preposition modifier, but it has a subtype which is only for this language. So we also have these, but you can also map them to some core which is shared across all languages. Okay. So the idea is to kind of abstract over the kind of differences in the different languages. You use the same set of post tags and like morphology. You have the same relations and the same heads. Okay, and now you have a consistent set of tree banks. Now, why is this useful? First, because now you can actually say, okay, so we parse like French, and we used a tree bank of like 5,000 sentences. And we got this accuracy, and we parsed Italian with the same like size, and we get that accuracy. And before, you can't really say, okay, so if we parse like French with 80% and like Italian with like 60, then like French is much easier to parse. Maybe it's only the choice of what you kind of represented that was easier. So now that when it's kind of consistent, you can actually compare accuracies across languages in a more meaningful way. Okay, and also if you want to say have feature based on that, or like write rules on top of your parse trees, now they can work better in more languages, or like with less tweaking, and also you don't have to learn a new label set for each language that you work on. And also there is this kind of idea, or like we would hope that we can now produce a parser that trains on some languages and then can be reasonably well on something that it didn't see maybe. Or maybe we can, so if we have like few data or like little data for some languages and like more data for other languages, we can somehow improve our parser by like showing it many different languages and see what happens. And also people who care about like language relations or how things influence between languages can also use that as a kind of a building block. Okay, so it's a very nice project which is kind of worth knowing about. And also it's nice because now you can download many different languages and work with them in the kind of same format. Yes?
Yeah, so these universal dependencies are really nice. I wonder, I've been reading a lot of recent dependency parsing literature, including yours, and all of it is evaluated on Stanford dependencies.
Yes.
And I guess that's because you want to compare to other works, but no one can break this spiral of it would be nice to see the performance in the papers on universal dependencies. So at what point are we going to switch?
Yeah, so the question was, most of the parsing world don't really use these. They use some other kind of set of languages or some set of parsers, and when will we switch to that? And you also pointed out that the reason for not working on these is that we want to kind of compare to like previous results, but we cannot break this cycle because, okay. So another reason that we don't work on these is that, okay, so now you have like 50 languages. It's much more time consuming to work on all of them. We have to choose a subset, and now which will we choose? So that's also kind of a reason, but not a good one, but a reason, okay? So I'm also involved in this project, and we are trying to kind of make it more kind of broadly used. There was a shared task this year about like parsing with these, and now there are results actually with that, and hopefully, you know, in a few years it will catch on and people actually compare to this and not to the older data sets. So yeah, we hope. It takes time, you know. Have to kind of, ideas are easy, having people agree on them, not so easy. Okay, so now we know what are the resources and like what we kind of want to do. We want to kind of get these trees, and the rest of this talk would be how do you actually produce such trees. Okay, and there are three main approaches to dependency parsing. Okay, like how do you get these trees? So one very common approach is called conversion, which is kind of, okay, you parse with a PCFG to a kind of a phrase structure, and then you convert these trees to dependencies. Like we've seen before, you just mark the heads, have the relations, and then have your trees. This actually works pretty well, but you have to kind of go through the other kind of presentation. So I will not talk about that because I already taught that to some extent, right? We know how to parse like with a PCFG, and we sort of know how to mark the heads, and now we can have at least the unlabeled structure already. And there are also kind of tools to do it for you. So yeah, so that's one way. And then there are like two other common ways. One of them is called graph-based, which is basically global optimization, which is very similar to what you have seen yesterday in the work about how to predict structures. And we'll talk about that soon. And after that, we'll also talk about re-decoding, which is what's called transition-based parsing, which is a different system of getting trees. So these are the most common approaches, and each one of them is a vast field, and there was a lot of work on each one. And there are like hybrids, so maybe you somehow combine this and that, or maybe you do this and then vote. And so like there are many different hybrids that kind of combine them. But these are the two main approaches, and which I will describe. And there are like many differences between them, basically. But like, so if you care about like machine learning and how to actually learn them, we'll cover these kind of differences soon, or how they work. But if you just want to use these parsers, then like something that you should know is that they get very similar accuracies these days, but like differently. So if you kind of use both and then vote between them, it will be even better. And that these guys are much faster usually because they are linear time and these are slower. Okay, a bit. Okay, now in terms of the technicalities, okay, so this is basically like you've seen in like such prediction. You define some function that scores sentence and tree pairs. Then you search for the best scoring structure. Okay, and of course, if you have simple scoring, it will be easier to search. Okay, And then greedy decoding is a different approach in which you start with an unparsed sentence, and then you apply actions to it incrementally until you have a parse. Okay, so this is a bit abstract. We'll talk about it later, and we'll see. But let's start with graph-based parsing, okay, which is, again, a very dominant approach for many years now. Okay, so what is the parsing problems more formally? So when we parse some sentence x, okay, so x is now like word sequence, or maybe words and post tags, we are looking over all of the trees that x can produce, so like over all of the trees over x, we want to find one tree for which the score of x and y is the best. Okay, so this is all of the trees that are available. So like say so if it's like a sentence with 5 words, then all of the trees which are projective that have 5 words in them. Okay, so that's our set, and we want to have defined with the best score. Okay, and when we train this thing, what we want to do, we want to do training such that our scoring function will assign a higher score to the correct pair than to any other pair. Okay, so we want to have a low score for bad trees, high score for the one good tree. Okay, and that's also what we did with the PCFG, but we didn't really train that. Okay, so we were looking for the tree with the highest probability, but we didn't say, okay, we train such that this will happen, but we just like said, this is how we kind of define our probabilities. So here we will kind of do this more directly. Okay, any question about this part? I think this kind of relates to yesterday, so you should at least be kind of familiar with that. Okay, now of course the problem here is this part. Okay, argmax over the kind of score of the tree in the sentence. It's a very hard search problem. Okay, because if you have arbitrary scoring here, then you have to basically go for each sentence and have, or like for each tree, and find its score and then rank. But like for every sentence, there are like very, very many trees, and you cannot really go over all of them. Okay, so you need to do something smarter. Again, like with Viterbi and like sequences. Okay, and the solution would be to decompose the score. So we are saying that the score of some tree y, okay, will be basically a sum of local score of parts. So we take y, we say y is now composed of different parts. Okay, and we want to score each part and sum them. Now we have a score for the entire tree. Okay, does that make sense? Now, of course, if you choose the parts wisely, then the search might be easier. And if you choose the parts in a way which is hard to search over, then the search will be hard. So the way you decompose and the way you search is very important, like very tightly coupled together. Okay, also the way you score, so your features. Okay, so let's go back to how you do static prediction. Okay, and this will kind of work for any problem in static prediction. You have some scoring function which is kind of decomposed over parts. So you basically decompose your structure into local factors, local parts. Okay, you assign a score to each one of them. Okay, and then the sum of the scores is the score of the structure itself, and then you look for the one that will maximize this. Okay, so that's how you predict structure, and this has like 4 components. So you need to know how to search. Okay, and this is kind of relates to how you decompose. So like, what are your parts? Each part you need to have to somehow represent in a way which will be easy to score. So basically, you take feature over the part, okay, and we'll discuss features shortly. And then, if you have features, you can then score them. Okay, so these are the components, and they all work together, but it's like 4 different parts. And now we just go over all of them. Okay, so in what we call an MST parser, or a first-order parser, okay, we say that the composition, okay, is into parts which are head modifier pair. So if you have like this sentence and this tree, okay, then we say that each arc, okay, from head to modifier will be its own part. Okay, so that's a part, that's a part, that's a part, that's a part, and so on. Okay, and now we have to basically find a set of good arcs that make a tree. We assign a score to each arc independently, and then we kind of find a good one. Okay, so our decomposition is over single arcs. Now this may sound like a not so great idea because it seems to be too isolated. So we kind of score each kind of arc independently, and indeed it is not the best choice. Or like a few years ago, people tried to kind of look at the larger parts and so on. But now with neural networks, it actually works very, very well. And we did not cover neural nets yet, or like LSTMs and so on. It will come tomorrow and the day after that. But I'm telling you, in kind of now the future, if you have like an LSTM over the words, then this kind of decomposition is actually very, very good because you get context from the other like LSTM part. Okay. So that was how you decompose. Okay. And to make it more clear, okay, the score of this tree, okay, will be kind of the sum of the score of Fox and they, and the score of Fox and who and likes and apples, and then jumped and Fox and jumped and over and so on. Okay, so you basically assign a score to each of these, and then you sum them, and that's the entire score. Okay, so that's the decomposition. As I said before, it may look very naive, but if you have good features, and in particular if you have neural nets, it works pretty well. Okay, so now how do you do parsing? So let's say your sentence is they ate pizza. Okay, so you have your root and then all of your words here. And you basically compute all of the possible scores under, over these items. So you want the score of 8 and day and 8, and pizza and day and pizza, and so on. Okay, so you have all of the possible score. That's n squared scores. So you basically just compute all of them. And once you have them, what you want to do is find a tree over these words that has the best score. Okay, so that's an MST problem, or the maximal spanning tree, or minimum if you want to kind of have the other way around. Okay, and that's almost an MST. Why almost? First, because it has direction. Okay, and an MST is undirected. Okay, so but we kind of have the direction here, so it's a variant of MST. And also MST will give you like all trees and not only projective ones. Okay, but you do have some procedure that will look over all of these kind of scores and find a good tree on that kind of is maximal and is a tree. Okay? And this is called graph-based parsing because you have this graph here that kind of gives you all of your scores or all of your possible relations. Okay. So that's how you decompose. That's how you kind of want to search. Now the question is like, how do you go from this to that? Like, how do you find your best tree? And that's this argmax. That's your search problem. And so doing search or finding the best tree, there are two common algorithms. For projective parsing, that's called the Eisner algorithm after Jason Eisner. Okay, and it uses this fancy dynamic program. And if you want to do non-projective, then you do this algorithm that's called Chulio-Edmunds or Tarjan. So these like this group and him have algorithms for spanning tree with directions. This one is a bit more efficient than that one. This is easier to implement. Okay, and I will not go into the details of them, but these are kind of well known in the literature. They exist, and you should kind of be able to implement. I will briefly describe this algorithm, okay, of how do you extract. I will not go into the details of why it works. It's a bit involved, and we don't have that much time. But I will kind of give it in a high level, and I will describe some of the intuition, or like what are the components, and then in the lab today you will have to implement it. So like you're right. So, but I think it's more important to be, like at some point, to be able to actually look at an algorithm and be able to kind of move from it to code than to actually understand how to develop it. Okay, because most of your work will be, how do I implement this stuff, right? And of course, if you know how to come up and kind of improve, it's even better. But given the amount of time we have, I think just like having the kind of high-level picture and be able to kind of move from it to code is the most important stuff. Okay, so what's the Eisner algorithm? It's find the best projective tree. And of course, we can actually use the CKY with the lexical items. Okay, so if you remember, CKY, given a grammar which may have words in it, okay, can find the best tree in n to the 5th thing, and some grammar constant. And if you just think about dependency tree as a grammar where you have the words, but all of the non-terminals are the same symbol, so you don't have s goes to n to 5th, but you have x goes to xx, okay, with some words on them, then you have a very small grammar, but with words, and then you can just like parse in n to the 5th. Okay, and the first parser actually did that. It's not very efficient. And then Eisner and Sata find a way to kind of reduce this to n cubed just by using some observation about projectivity and about how these trees nest or how do they behave. And the main idea, which I will not go into the details of, is that they wanted to kind of isolate the kind of two sides of the tree. So if you have a world and it has like children to its left and to its right, you can say, I will first do all of the left ones and then all of the right ones, okay, in some order. And if I kind of look into that, I can be much more efficient in how I do my search. Or I can kind of make use of this fact to kind of reduce the space. Now, JSON has a very clear way of explaining this. It takes like an hour though, so I will not go into the details. I will just like give you the actual algorithm and how it works. So like any kind of algorithm in DP, you take small parts and you combine them into larger parts. Okay, and what I've shown you with CKY is you have like two triangles that kind of form a larger one with some rule on top, right? And what happens here, so we have both triangles and trapezoids, and they may have sides. Okay, so now I'm showing you only one side, okay? But there is also the kind of mirror of that. So here we have like left triangle and like right triangle, and we have this trapezoid, okay? And we also have the other way of the trapezoid. Okay? And basically what you can do is if you have a triangle from some location to some other location, and then you have some other triangle in the other direction from the one after that to some other span. Okay? What you can do is you can add an arc between head and modifier, these are two ends, okay? And build a trapezoid. Okay? What do you do with this trapezoid? You combine it with some triangle, which is in the same direction, to build a larger triangle. And notice that when you kind of moved from this to that, you forgot what this arc was because you already know it. Okay? So the algorithm, what it will do is basically start with many triangles and then combine some of them to form trapezoid, yeah? And then do some more combination until you have like one large triangle over the entire thing. Okay? And now, if you want to kind of score things, then whenever you combine two triangles, your score is this arc's score, okay, from H to M. Okay, and that's the score we defined. And when you combine triangle and this trapezoid, then it's a 0 score because you don't add any more arcs. Okay, and now what you're looking for is basically the best way to combine small triangles somehow two trapezoids and like larger triangle into a huge triangle. Okay, and what's the best way to do it? Okay, so let's kind of give you some kind of how it runs. So you have this sentence, and initially each word has two triangles. Okay, one left and one right, and the root has only one triangle. Okay, because that's kind of it will kind of collect the kind of last thing at the end. And then at first, okay, you took like these two, okay, and you say, okay, so I will connect them with a trapezoid by basically adding an arc from this to this, okay, and you can also connect these two and like these three, okay, and have all of that together, okay, and then you kind of combine this and that into like a triangle and and this and that into this and that into a triangle, and then a trapezoid and triangles and so on. Okay, so that's how you kind of build your thing incrementally until you are left with this triangle. Okay, so again, I'm not really going over the actual process, but the idea is that you have two structures, triangles and trapezoids, and each one of them has a direction, and each one of them has endpoints. Okay, you want to know where it starts and where it ends. Okay, and at each point you can see what you can combine to have larger parts. Okay, so basically you start with two triangles for each word. You combine two small ones into a trapezoid and add an arc between the words. You then combine trapezoids and triangles to have like larger triangles. Okay, and you just have to make sure that the order in which you do this is that you build all of the small things before the larger ones. Okay, so like if you want to know what are all of the ways that I can say build this like trapezoid, okay, so it will be either like this triangle and this triangle, or this triangle and this triangle, and so on. Okay, so once you kind of come to build this, you have to make sure that this and this and this are all computed already. Okay, so you have to make sure all of the kind of small parts are done before the larger ones. And this all boils down to this algorithm. Okay, so it's basically two loops, and then it's max, which is another loop. Okay, and you just have to kind of try and go from this to code at some point in the lab. Okay, just to kind of so it will be easier to read. So L is a left item, either left triangle or left trapezoid. R is a right item. C is a triangle, which is called complete, and I is a trapezoid. Okay, so if you want to kind of map between this to that, then okay, that's the way to do it. Basically, you're saying, okay, so if I want to kind of build this structure, okay, which is incomplete left from point S to point T, okay, then its score would be you combine the complete and the right with the complete and the left, so like two triangles, okay, together. And this one is from S to R, and this one from R plus 1 to T. So these are S and T, and the R just like do a loop and find all of the possible R's and combine them. Okay, so that's this algorithm, and just like fill this table, and at the end you have the kind of score of the kind of best one, and if you keep back pointers to where you came, then that's what you need to do. So it's a nice challenge to actually implement that. If you don't get to it, then it's also fine, because like you can find this code online. But it is a nice kind of challenge to kind of try to go from this to code, because it's happen often. Okay, so now we also know how to do search, or sort of know how to do search. We know that we can do search. And now let's talk about how do you represent each part. Okay, so we say that each part is an arc, okay, and we have to score it, but before scoring, we had to kind of say, okay, how do we score an arc? Like, so if to assign a score, we need to look at some features of the arc and then kind of assign a score to each feature and then have the sum and learn and so on. Okay, so this thing here, phi of the part, okay, or phi of the arc is the feature function that extracts all the signals from the part. And most work goes into this component. Okay, so you have a nice model. If you have bad features, it will not work well no matter what you do. So you need to have good features to score with. Okay, and if I were giving this talk like 2 years ago, I would spend a lot of time on these features because they're actually very, very important. Now I'll spend a little time, and I'll tell you why in a minute. So let's have a linear classifier, okay, and you want to score this arc, so from so to with, and these are the post tags, and this is the sequence. So our features for so and with could be, okay, so we know, so they could be based on this word and that word. So we know that, okay, so the head is so, the modifier is with, maybe the pair head modifier are this and that, maybe the post tag here is verb, and that's a proposition. That's also important to know, okay? We can also look at the words around, so like John and Mary are also important to this so, and like yesterday and his may be important. And like maybe this like tag sequence over here, RP, PR, and NVN could also be important, and so on. You may want to kind of count how many words are in between, so like what's the length of this arc, or what post tags are in between them, it's also important, okay, and so on. And also you want to combine them, okay? And a good set of features will look like that, okay? It's messy, people work on it a lot, okay? And that's from a good parser that people worked on. But these days I will say, okay, forget about all of this, like it's kind of how to do it, it's important, but we get better results if we actually use some neural net. That's with a paper kind of recent for my group with Eli Kipper-Wasser. So what we show here is that if you take a BiLSTM over all of the sentence, so here it's in gray, so you don't see it, but the sentence is here, and you don't know what a BiLSTM is yet, but it's some neural network that kind of goes over all of the words, okay, and basically will produce one vector for each word, okay, and this vector captures the word in context, okay, and you will learn about it in 2 days, I think, from Chris Dyer. So if you have this BiLSTM encoding of the sentence, okay, then you can just say, I'll take this vector and that vector and concatenate them, and that will be my features for this arc, okay? And if I want to score like this arc from here to here, I will just take this vector and that vector and concat them and score them and so on. And then it's the BiLSTM's job to extract what's important about this pair, or like about this word and its surrounding, or the kind of distance between them based on what it does. And it actually does it pretty well. Again, it's a bit hand-wavy, but kind of, I think the common understanding now is that BiLSTMs are very good at finding good features for arc factored parsing, for like this form of parsing. So again, previously you had to do this, now you can do that, and all of the smartness goes inside here and actually works very, very well. And I hope you will understand it better in a few days. We kind of debated what to do first, this or that, but I think we can do this before and then kind of have you a teaser for like, why do you want to learn about neural nets? Okay, so now we know how to represent things. And now the question is, okay, so how do we actually score them? Okay, so we have these like vectors, which can either be like just like this concatenation, or maybe we have like a vector where like each dimension is like an indicator, and we have like these. Okay, so there is a mapping between part and features, and like a vector. How do we score? How do we send a score to the part? And in a linear model, it's very like I said before, we take this like feature vector of the head and the modifier, and we use this weight vector, which would train, that will assign a score to each feature or to each dimension, and then sum them. Okay, so it's this dot product between weight vector and feature, and that will be a linear classifier. Okay, pretty much like you've seen yesterday. You can also have a non-linear version where you basically just take this and have some hidden layer and then some kind of vector for scoring. Now you have more parameters to tune. Again, this will become, I guess, clearer tomorrow where you see neural nets. Yeah, it's just like a kind of small elaboration on that, which works well. And then also there is something which is called a bilinear form, and which works very well if you have this bi-LSTM representation. Okay, so what it says, so it's called bilinear or bi-affine. It's also a name. What it means basically is take features based only on the head. Okay, multiply them by some matrix, and then have your features based only on the modifier. Okay, and now you have this like single score. Okay, and if this and these vectors are these bi-LSTM vectors, so this and that, then all of this thing learns how to work well with this and get very nice kind of expressivity. Okay, again, I think it will be more apparent tomorrow, but these are kind of ways to score that people use these days. Until very recently, that was the only one people use, so I will continue on that. But moving from this to this is very, very simple, and this is also not hard to do. So we should just kind of be aware that these things are available, and like in new papers, they use those. Okay, so we know how to score now. We have it, yeah.
Maybe I missed it, but how at that stage you decide what is head and what is modifier?
So you ask, how do I know which is head and which is modifier? Okay, so when I score this arc, then I say I assume this is the head and this is the modifier, and what's the score? So if this was the head and this was the modifier, what are the features and what are the score? Now, when I score this arc, it's the other way around, and then now I assume that this is and that's the modifier, and like so here I will just basically have this feed over here and this feed over there, so it's the other way around. So the order matters, right? Okay, and I will assign a score to each one. And each one of them will have a different score, and then when I find the best three, obviously they cannot be together because it will be a loop, so I have to choose one of them.
And what is, and you do this for all words in a sequence?
Yeah.
Without like taking into account what part of speech is this? If, for instance, if it's like conjunction, or it cannot be had anyway, why do you need them this pair?
Okay, so now you're saying I know some stuff, like I know that if this word is a determiner, then it will not be the head anyhow, so why do I even care? And I could find rules and kind of prune stuff away, some people do, but it's really hard to find, these very hard rules. And sometimes, you can find something which is often not the head as a head because like something is weird in that sentence. So I just let our learner figure it out. So I do have like post tags here as features or as like part of the features. So if it is very uncommon for a like determiner to be head, it will just receive a very, very low score. So it might be kind of a bit more time to work on it when computing, but it can learn that. So like so if our rule is this never happens, then it's very, very easy for the learner to actually learn it. So why not let it just learn it? Okay, and maybe be a bit softer than just never happens.
Just thinking that you can somehow like say that in the net that this is please be attentive to the scores. This is the verb and this is a noun. It can be most of the time.
It does know that like this is a verb and this is a noun. We do feed it into the network, and it kind of does use that. We don't feed hard rules like this can never happen. It just say okay, if this is a verb, this is a noun, it will kind of see if it happens a lot or not, and then decide on the score, if it learns well, and it learns well, so very good. Okay, so that's how we score. And now how do we train this thing? Okay, so like we train any other like network, or like any other classifier. So now I will give you the linear version, because that's what you learned yesterday. Okay, so basically with the same algorithm, Perceptron. Okay, so basically we go over each gold pair of x and y, so the sentence and like the right tree. Okay, for each one we predict our best guess based on x, okay, and our current w. So basically we say, okay, let's score all of the possible head modifiers based on our features and our kind of weight. and then we find the best tree according to our current model. Okay, and now we have this prediction, which is a tree. And this prediction may be correct, and then we just move on to the next one. And if it's incorrect, okay, then we do an update. So what's the update? We basically take our weights and we add to them all of the features from the gold tree, and we subtract all of the features from the incorrect tree. Okay, and these things may cancel out if it's the same edge, right? So it will be okay, and otherwise we kind of just do the update. So that's basically what you've seen for post-tagging, but the only difference is now this argmax is different, and the parts now are not like pairs of kind of words which are consecutive and tags, but they are actual like pairs of words. Okay, so that's for Perceptron. You can easily extend this to do like max margin or like CRF less easily, but you can extend it. Just like change this update rule, and if it's a neural net, then it's not really this update rule, but like a backprop kind of thing, which you'll learn tomorrow. But it's also very easy to plug it in. Okay, so basically you have your gold, you have your prediction, okay, and then you have a loss which is based on the two trees, and then you do update based on the loss, okay, and that's the update for the perceptron. Okay, so I think now you can implement this kind of thing, and you actually will implement it for a simple case this afternoon. Some of you, yeah.
How do the dependency labels go into this?
Okay, so yeah, so there are no labels over here. If you want to have labels, then basically you say, okay, so now my part is not head modifier, but head modifier label. So now we have, and you may say that it will kind of make larger space, but not really, because like if you have head modifier label, okay, and you have like for each head modifier all of the labels, then only one of them can be in the tree. So you can just like take the max over each head modifier pair, and like that will be, because there is no way where you say, okay, so with one tree, I will prefer this label over the other because they're independent of each other. Okay, so it's really kind of easy to add it in. There are also other ways to add labels. So like something else you can do is first do unlabeled parsing and kind of do this, and then based on the tree you got, you can now say, okay, so this arc in its kind of with its children and all. Now let's classify what its label would be, which also works very well. So you can just also add them after the fact with an extra classifier. Okay, so these are the two ways to add labels to this. Other questions? Great. Okay, so just like to be clear, these are the gold features. These are the ones which are predicted. You want to go for the gold against the predicted if they're wrong. So that was how we train, and finally at parsing time, what we do, you assign a score to each head modifier pair according to our model, okay? And then you use either Eisner or CLE to find the best scoring tree, and that's it, okay? And you may add some like label on top to have like your labels, but yeah. Okay, so that's how you do parsing. So that's the graph-based model, very, very common, and ties very, very nicely to how in general you do this structural prediction. So it's very, very similar to what you've seen yesterday for like sequence tagging, but the parts are different and the features and the search are different, but it's the same framework, okay? and it works well. Now let's move on to something very different, which is called transmission-based parsing. Okay, and this kind of algorithms is very different approach to parsing, which also works pretty well. So the idea here is that you start with an unparsed sentence, and then you apply some locally optimal action until you have a good parse. Okay? So like one difference that we kind of see already is that there you kind of looked for the best tree overall. Here you just like do greedy steps and hope for the best. Okay? And the other difference is previously we basically had parts and we had a score for each part. Okay, and then we kind of looked for like good parts overall. Here we don't have parts, we have actions. Okay, so we will assign score to action, which will then produce a parse tree. Okay, and the benefits of that is that now you can use all of the features you want. What do I mean? So if before all of our parts were like these arcs, only had modifier pairs, then all of our features were kind of restricted to thing over this arc. So you can say this is the head, this is the modifier, but you cannot say this is the head, this is the modifier, and the head of the head is some other words because it's not part of your part. Okay? But if you do this greedy thing, you can do whatever you want. Okay? You don't have this kind of restriction because you don't have this part decomposition. And it can be very, very accurate, surprisingly so. And it can be very, very fast because it's a linear time, not n cubed. Okay. So the way it works, and that's the kind of overall story, which is a weird story, I'll tell you up front. There is some machine, an abstract machine, that has a stack and a buffer usually, and it is initialized with all of the words in the sentence. Okay? And then you have these actions which you can apply, and whenever you apply an action, it affects the words on the stack and the buffer. It kind of moves them between the stack and the buffer, or like removes them, and so on. And it also adds links between words. And at the end, you are left with a parse tree, like after you apply action after the other. And there are many ways to choose which actions you actually have. And each set of actions and their semantics define one system for parsing. So there are many different parsing systems under this framework, each of them with a slightly different set of actions. Okay, but we'll describe one system which is called arc-eager, which has 4 actions. Okay, so the first action is called shift. Okay, and what shift does? So here we have our stack drawn in gray and our buffer drawn in white. Okay, and we have some word on the stack. It could be more words, and we have some words on the buffer. Okay, and what shift does, it moves one word from the buffer to the stack. Okay, kind of similar. There is some precondition here is that the buffer is not empty because otherwise you cannot shift. So that's the shift action. There is also a left arc with label action. So what this does, it will add an arc from the top of the stack to the top of the, so from the buffer to the stack. Okay, so it will add this arc. And it will also remove this word from the stack. Okay, so now something in gray is no longer on the stack. So now the head is this guy, but I don't kind of remove it completely because I want to kind of keep the arc over there. So you add an arc, and you remove from the stack. Okay, and it can also be like a left arc and a label, and then it will be a labeled arc, and you have like 10 different actions, like so you have a left subject, left determiner, and so on. Okay. Right arc, what it does, it will add an arc from this to this and do a shift. Okay, so you start here and then you get to there. Okay, so a new arc and then a shift. And then finally reduce. What reduce will do is it will take the item on the top of the stack, which has a parent already, and it will kind of pop it from the stack. Okay, so now you have A as the head. So this is our 4 actions. Okay, and someone, Joachim Livre, it's the one, came up with this system. Okay, and he proved that this system is complete in the sense that it can produce every parse tree, and that for every parse tree you can find a set of solutions that will produce it. Okay, and it also and it will produce all and only projective trees. Okay, over the sentence. So now let's see an example. So you have your stack and your buffer, and you initialize the system with everything on the buffer and nothing on the stack. And then you apply a shift and a left and a shift and a right and reduce and right and right, and now reduce and reduce and reduce, and now you have an empty stack, empty buffer, and the tree on top. Okay, so you basically start with your kind of initial configuration. You apply things until you reach an end state, which is basically both are empty, and you have the tree, and then you have the tree. So that's our parsing system. And we know, because someone proved it, Joachim, that every sequence of action will result in some valid tree structure, that every structure is derivable by at least one sequence of action. There may be a few. And we also know, given a tree, what is the sequence that will produce it. Okay, that's actually pretty easy to do. If you kind of try, you can say, okay, so if that's our tree, okay, so we want 8 and she and 8 and pizza and so on, then you can say, okay, so if I'm starting here, then I must shift, because that's the only thing I can do. Now I should do a left, because otherwise I can not do it later, so I'll do a left. And then I basically must shift. And then, okay, I need to do a right, so I'll do it, and so on. So you can derive this thing informally or more formally, but it's easy to get from a gold tree to what is the way to produce it. Okay, so that was one system. There are also other systems like arc hybrid or arc standard, which is kind of small variants with slightly different set of transitions. And for each of them, we can know that it will derive all trees and how to get it to work. Why do you want to choose one system and not the other? Actually, no good reason. Like some of them work some better for other languages and so on. It's mostly empirical. Some of them do have like properties which are nicer to work with, but let's work with this one for now. It's very common and it works well for English. Questions about this part? Yes.
Is it just working for English or other languages as well?
So this system will work for every language that is projective, okay? Because it can only do like projective trees. There are variants that are also non-projective. So this framework will work for any sentence. I will give examples on English because that's what we all know. But also the graph system and also this one, it can work for every language, okay? If we train a parser for it. So if you have a tree bank, you can for each sentence produce this like action sequence and train, and it will work for it. Again, it might be better for English and works for others and so on. But it works pretty well on all of them, and we get good results from many languages. Other questions? Yes?
How do you order the neighbors? You have several alternatives, I suppose.
What do you mean order the neighbors?
When you are choosing which rule to apply, which action.
Okay, so the question is like when I choose which rule to apply, how do I choose so if now I can apply two different rules, like both shift and reduce, which one will I do, right? So it depends on the system. For this system, you can say when I'm kind of asking what is the oracle sequence, like what is the one that I want to train on, okay, you can say if I have two options, I will always use shift before reduce, or reduce before shift, okay, and that will be my kind of canonical order. And if you do that, and you kind of prove that that they can both work and you will not get stuck, then great, you can do it. And then one of them will work better than the other. So just choose that one that works better. A better approach maybe, which I will not describe today, is to allow both of them. So if there are several options, just like ask the classifier, which is more natural to it, and just use that. So that's called dynamic oracle, which I worked on a bit, but we can talk about it later if you want. But for now, let's assume that you have like one order which you can choose. And if there are if you don't know if you want to shift or reduce, you say in training I will first shift and then reduce, okay? And at test time, the parser will just decide what it wants to do. Okay. Other questions? Yes. So if you need to have this kind of arc from this left, then if you do it early, it will not stop you. So you will not get stuck. And if you do a shift, then you may lose this. So you want to do a kind of left at this point. Of course, that you know as a human if you know what the gold tree is, right? So if you know how the tree looks like, you can easily come up with the sequence. If you don't know what the tree looks like, then yeah, I mean, you have to choose somehow, and we'll talk about this later.
Oh, okay. So it's not like I shift and then the only thing that I can do is do a left and then
No, you can do like shift, and then right, and you have like this weird tree. Okay, it will be an incorrect tree, but it can happen. So I mean, again, you can choose whatever sequence you want, and it will give you some tree, and most of them are wrong, and only one sequence is actually correct. So you somehow need to choose which one is correct, and if you know what the tree is, it's very easy to come up with the correct one. If you don't know what a tree is, well, that's what you have to learn.
But there is no post tagging behind this.
So the words do have post tags, but they don't have to. It's easier for the features if they have post tags. Okay. Other questions? Okay. So now that we know that we can find an oracle, let's see how we parse, or like what's the algorithm for parsing if we have an oracle sequence. So we know what the kind of right set of actions is. So if we know, so we have this oracle that we apply to the sentence and the tree. Okay, and now we have this sequence of action that will produce this tree for the sentence. So now we initialize our first configuration, basically everything on the buffer and empty stack, okay, from the sentence. And then while it's not final, what we do is take the next action from the sequence, okay, and we apply it to our configuration, get a new configuration, and we do it in a loop until we are final, and then we return the last tree from this configuration. So that's the pseudocode. It's easy to implement. And now let's run it. So okay, so you start. So that's your sentence. You get the oracle sequence. So that's this. So this is what you need to apply. You initialize your configuration. Now this is not final. So you do next action, then you apply it. Next action, apply. Next action, apply, and so on. Okay, until you are done at the end, and now you can return this tree. Okay, now, so this is the parsing algorithm, and it's great, but the problem is that, okay, so you need to know what the next action is, and for this you need the sequence, and for this you need the tree. So it's not really useful to parse if you know what the tree is, because you know what the tree is. Okay, so why do you want to parse to begin with? So what we do here is basically we use this thing for training, so that we can then do things without knowing what the tree is. Okay, so what we want to do is start with some weight vector, or like some parameters. And then instead of taking the action from the sequence that depends on the tree, what we want to do is to predict this action based on the configuration that we are at now. Okay, so we assume that there is some relation between what we built so far and what we see on the buffer and the next action. Okay, so we assume there is this relation that like if we are, say, in this configuration, right? So we say, we see 8 and she and pizza reduce and like quit there. Okay, so we have like this tree and this stack and this buffer. Then we want to do right. Okay. Why do we want to do right? Because it kind of makes sense maybe to do it. So we assume some connection between like this configuration and the next action, or that you can kind of guess one based on the other. And I think it's a good assumption to make. Okay, so then what you do is you summarize somehow your configuration, okay, with features. So you say maybe we have this word on the top of the stack, that word one below it, that's the buffer. We have left modifiers and like right modifiers and like post tags and so on. Basically, define features based on your configuration. Again, if it was 2 years ago, I kind of go in depth, like how do you define them. These days, you do the same trick and use the BiLSTM of the words and kind of concatenate a few, and it works very, very well. But I will not kind of go into the details of this now, but you somehow define good features, and then you predict. Now, what's predict? It's some classifier. So it could be, so it's basically a multi-class classifier, right? You see a configuration, and then you want to choose among 4 actions, or like 50 actions, right? So it's like multi-class, but you do it over and over again, okay? And you can use there whatever you want. You can use SVM, you can use large margin, you can use Perceptron, You can use neural net, whatever you want to do this prediction. Okay, so that's how you parse with no oracle. Now, how do you train it? Okay, so first what you do is you summarize your configuration with some feature vector. Then you predict based on the features, and you need to just learn the kind of correct weight or the correct model. So how do you learn it? So you start with this parsing with oracle. So now we have the sequence, we have the tree, we know what it is, okay? And we have this algorithm that will kind of produce trees based on this, okay? That's what we've seen before. And we kind of make some space here, okay, and add this part. Okay, so what we do is, okay, so we start with some initial weight vector, and if it's linear, then it could be 0. If it's neural net, it will be some random initialization, okay? And then we go over all of the sentence tree pairs in our corpus that we know, that the gold ones. For each one, we get the gold tree from the kind of pair. We have the now gold sequence, so we know what we need to do. And then we initialize, and while not done, we say, okay, what is the next action? What is the kind of gold next action? Okay. Now we take features from this configuration, and we predict, right, based on our kind of configuration. And now we see if what we said is the right action is actually the right action. Okay. And if it is, we're happy. If it's not, we do an update. Okay. And how does this update look like? Like any update that we've seen in the previous days. Okay, so it could be like W plus these features minus those features, or it could be something more elaborate. So you do some update. Okay, and then you apply the right action and go on. Okay, so the idea is that you basically now you kind of go through the kind of right sequence, and at each point you see a configuration, and you see what the right action is, and that's a new example for training, right? You just need to add it to your classifier. So you do it like in a loop, and after a while, you'll learn good weight if you have good features. Okay, and then at parsing time, you just have to predict. Okay, so if we summarize this part, basically you summarize the configuration with a set of features, and you learn what is the best action to take at each configuration. And you hope that this will generalize well. Like you hope that your features capture aspects of the configuration that if it will see similar things, it will know what is the right action to choose. And if you apply these things in sequence, you'll get a good prediction. Of course, this is a bit tricky because you make this assumption here that every action is correct. And once you made a mistake, then you may not be able to kind of continue very well from this, okay, because you do like greedy, and like one mistake can kind of really screw you over. But you assume that you learn something which is good enough so that you don't make that many mistakes. Of course, there are ways to improve this, which I'll briefly describe in a minute, but not go into the details of. Okay, so basically, this approach is a very different approach to parsing. So you don't score parts and then kind of look for the best thing. You score actions and you do them greedily. However, it's a very common approach, and it can be as accurate as the other techniques. Okay. Well, some things can be a bit better, but now they're very tied. Like it's really a very tied approach. It's very easy to implement because there's no search, nothing. You just have to kind of know what your system is and just like train it. It can be very, very fast, like O of n, okay, because it has to do, like for an n-length sequence, it has to do like 2n actions at most. So it can be very, very fast. And it can be even further improved. So there's something called easy first parser, which I did in my PhD, which is basically don't go left to right, but in some better order. More importantly, there's this thing called dynamic oracle, which means train the parser such that if you made a mistake at the beginning, it will know how to recover and do the best thing that it's still possible. And this works, this helps a bit and kind of gives you 1 or 2 extra points So you should try that. If you care about learning, and then kind of look at these papers, you can ask me later and kind of point you and see how it works. If you just use a parser, then you may want to use one that does this because it will be more accurate. So kind of look for this feature. And you can do a beam search, which basically means I don't kind of only build like one set of actions, but like several in tandem, and then I kind of at the end choose the best one. Okay, so that's a bit slower, but also works well. You should like add search to it, like small search, not exhaustive. And that's also a thing that you can add if you know how to do beam search. So it's kind of orthogonal. Yeah. So to summarize like the entire kind of part, we talked about syntax and hierarchy and like structures. And we kind of said why syntax matters and why do we want to use it, and I hope you were convinced. Then we've seen grammars and PCFGs and SQL algorithms. So how do you actually parse with these, and what are grammars? And then we talked about headwords, and then these were connected to like dependencies. And then we saw how to parse with graph-based and with region-based parsers. Now, to kind of wrap this up, I'll give you a few pointers on how to actually apply parsing. So if you want to write the code, great, you kind of know how to do it now. If you just want to use good parsing algorithms from other people, then that's the way to do it. Now, I also tell you that like there is some like large gap, or a gap, not very large, between kind of knowing the algorithm and having a good parser. Because you do have to be careful, you know, with how do you actually do your features and your learning and to kind of tweak it. And like it's very easy to kind of produce a parser. To produce the best parser, you have to have some more work, like everything in life, right? You can do like a good solution, but if you want to do it like best. So if you just like want to use a parser, use something that like people had before and it will be better. Okay, so for the phrase-based stuff, you want to check out the Berkeley parser and one from Stanford. So this is using the state split approach, like at the end of the previous talk, where you kind of each state is like split into very different sub-states, and it works very, very well. This guy keeps changing what they're using, so I'm not sure, but it's also it's a good system. And if you have a grammar that you kind of wrote or kind of have by hand and you just want to apply it, then there is something called bitbar that can also do that. So it's also possible. Okay, but these are strong parsers, and I think in the next year we'll see some new strong ones which will kind of be available because there are advances, but no package that I know of yet. For dependencies, you may want to use Stanford. Again, I'm not sure what they're using these days, but it's a good one. Or Spacey. So Spacey is a nice Python-based parser, which is not really trainable, but it is very, very strong and very, very fast, which is based on these transit systems. Okay, so it's very fast. It's robust. It's only English though. These are kind of for several languages, but not all of them. If you want to train a parser, then this is trainable on whatever you have, and so on. And then if you want to do like dependencies and research, meaning that you want to have a dependency parser and then train it or change it or whatever, then there are many options available, but I'll list two. So two neural parsers that work pretty well. So that's BEAST parser from my group. And that's, we have one graph-based and one resistor-based system in this, and it works very well with BiLSTMs. And then there is the Stack LSTM from Chris Dyer group that also does an LSTM-based thing with transition. Both are kind of easy to change and easy to train. So if you want to kind of explore parsing, these are good options. If you want to use parsing, these are good options. Thanks, and I'll take questions now or later. So, question? Yes.
Actually, do you know how this dependency parsing can be applied for polysynthetic language?
I cannot really hear you, so let's wait for the mic. Okay, now it's solved. Yes.
Can you tell me, please, how this dependency parsing can be applied to polysynthetic languages? So if you have the word is equal to the sentence.
Words that I cannot really.
There are like Native American languages. That's the whole sentence is one word. In the
Okay, so if the whole sentence is one
there
word.
any kind of methods? What was you said that universal dependencies are trying to make the whole like schema for all languages, but like there are thousands of them, and like polysynthetic languages, they have this quite not usual for us.
Okay,
now,
so
for
you're saying that that there are languages
how
in which.
people do this? I mean, how people do the
Okay, so
universal
okay,
dependencies for
so
them.
let's kind of so everyone will hear. So the question is, there are languages in which basically one word keeps a lot, and even kind of in the extreme, one word is like all the sentence. Okay, and how do you parse them? So first, if one word is really all the sentence, it's very easy to parse. It's the root, and that's it. You're done. But of course, that's not the right answer, right? So the right answer is you have to define words differently. So these words basically have different units in them, right? And these units with morphology kind of create a tree on top. And then the parser's job would be to first split this into like components and then combine them. Okay, so how to combine them, I've kind of talked about. How to split, I didn't, because that's kind of language dependent. And what you really want to do is do them jointly, right? So you want to both split and parse at the same time. And there are some works that try to do that. I did not go into the details here. Say in Hebrew, which is what I kind of speak usually and also work on sometimes, there is this case that like some words are actually multi-word tokens. And there you want to kind of split these but not others and do. And we do have parsing algorithms for these. I think they can be extended to other ones. But of course, if you have something like Finnish or like German, where like each word really carries a lot of kind of material, then you have to first split and then parse. Okay. Yes?
More questions? Hi. So I believe a modification of this biased LSTM parser has now 95 F1 score on Stanford, using Stanford dependencies on Wall Street Journal, right? Is there still some work to do? Is it, are we finished with dependency parsing?
So the comment here, when we parse the Pentribank, which is kind of a common benchmark, we get to very high accuracy. We get to like, you get the right head like 95% of the time. So we're kind of really kind of near the ceiling of what we can do on this benchmark. And in one way, I say, yeah, parsing is solved, use it, like, and let's kind of continue. On the other hand, parsing is not solved because first, on other languages, we get much worse results. So like, there was now this shared task for like UD, universal dependencies, and there the kind of average score is about 85, I think, for the best system. So there is a gap. Now, while other languages are worse, first maybe you have these things where you have to split words maybe, or like you have larger vocabularies and you have like worse post-taggers and so on. And maybe you just have like less data. So like what do you do if you don't have data? So in English, there is a very large data set, so we can kind of use that. Usually it's smaller, so you have to somehow do this. And also within English, we are very good on these data sets, which is kind of news. When you move from this to parse blogs or Twitter or emails or legal documents or chemistry papers or many other things, then you also drop. So how to actually do good parsing outside of your news domain is also a very big question. So like these are the kind of open research questions. And one way to solve them is just basically, okay, so create 3 banks and it will be solved. And if you have like money to do it for everything, then yeah, we'll solve it. For most of us, we may want to have a way to somehow transfer knowledge between these kind of domains and do it in a kind of without kind of all of the annotation. And that's a very open and very useful research area.
More questions?
Thank you. For transition-based parsing, how do you deal with multi-word expression? Because the whole expression could be a head or a modifier.
Okay, so the question was, how do you deal with multi-word expression, which is basically the opposite of her question. So she said that there are some words that are actually many words, and you said, okay, so there are some sequences which are actually one word, right? And it's true, there are some. Actually, the question is not about like transition or graph, it's for both of them. You want to somehow mark that like these things are one unit. Okay, one way to do it, which people usually do these days, is just say, okay, so we have a relation that marks part of a multi-word unit, and you say that like every sequence which is one kind of unit in your definition, you will do its annotation as like a sequence of like everything depends on the first word, okay, with this MWE label, right? And then you just kind of recover that and just like parse as usual and hope for the best. Now, it may or may not work for some cases, and you may want to kind of add some dictionary maybe of these words or do something fancier, and that's people are still working on. But like technically, you just like say, okay, this whole thing, everything depends on its head, and only the kind of first word has modifiers and so on, and that's it. Does that answer your question?
Yeah, thank you.
Okay.
Hi, first of all, thank you for your talk. I'm thinking about like dependencies might be revolutionizing the parsing word because they are probably more efficient since you have binary relationships and not things like trees. However, I have the feeling, it might be that I am out of date, but I have the feeling that there are some applications that still need phrase-based structures, like, I don't know, co-reference resolution, might be name entity. So you think, it's more like a personal question. You think that there should be something to convert dependencies into phrase-based structures, or you think that it should be like dependencies should like mark now the like should revolution, like, I don't know, revolution everything, and then all the applications should be like be developed in like based on dependencies?
Okay, so the question was, we have dependencies and everyone uses them, but we can also use like phrase-based for other stuff, which is also useful. And I mean, I agree there is a reason I taught like the first half about like phrase-based. People still use them and they're still useful. You may want to kind of choose what you want to do. Okay, I'm not saying like one is better than the other. Maybe it's a bit faster to do dependencies than like phrase-based, but if you need phrase-based, just like go ahead and do it. There is research that kind of tries to see, okay, that's a dependency tree. Let's try to kind of convert back with some learning approach to phrase-based. People do this for speed, but if you can kind of have the time, just like have a good kind of phrase-based tree to begin with and to be good for you. So it's really based on the application. But also, you can extract a lot of kind of phrase information already from the dependencies. So if you care about the spans, but not the labels of the spans, then you have enough already, because you take the head and all of its modifiers kind of recursively, and you have a span. So for NER, this could be enough. Like you can actually use that. For Coref or for SRL, you may want to have something which is more fine-grained and also know actually what the labels are. And then, yeah, you should use just phrase-based. Or you can actually use both if you want, right? And kind of, so I'm not saying use either this or that. They are both useful. They are both accurate these days, thankfully. So, yeah.
More questions?
I think there's some in the front. Okay.
Okay, let's do these and then that.
Yeah.
Thank you. So it was a very, very nice talk. Indeed, dependency structures are, like you mentioned at the beginning, that now dependency structure are kind of like consensual, but indeed the actual linguistic theories behind might vary a lot. And indeed some linguistic like theory don't really use trees, but more complex graphs to represent the syntactic structure. So maybe at some point it was intractable or whatever. But now that we have more computational power, do you think that like the dependency community will go beyond that and try to make more complex structures, or will we stick to trees?
Okay, so the question was, to summarize, if I get it right, I've been talking about trees. So in the first part, it was like phrase-based trees, where all of the words are given, there are no empty elements. Okay, and now in the second part, I had like dependency trees, and there were trees, there were no cycles, and like no multi-parents, and so on. And for some structures, or for some instances, we actually do want to have empty elements, or we have to have like a non-tree, like a graph structure of the sentence. Okay, so why don't we do this? Like, why do we parse for two trees? Okay, so the first answer is that trees are much easier than graphs. Okay, and that for the most part, they capture most of what you want. But yes, the actual future is going to graphs, which are more expressive. People are still debating on what is the right structure for the graphs. Okay, so we still talk on that. In UD, there is definitely an effort to add some extra arcs which do make it non-trees, so it's not focused only on trees. So we'll see many more non-tree structures later, but like almost tree maybe, but like with some extra arcs. And yes, it's currently an ongoing research to try and parse efficiently or well enough to graph structures. So that definitely is coming in the future and actually started. So like for several years now, people are working on graph parsing.
So there was a question in the front.
Hi, thank you for the talk. My question is related to ontologies, since we can use an application of using dependency trees is to identify meaningful relations between concepts. Do you think this is a good approach for this type of task?
So because you want to build ontologies?
Yeah, let's say that I have a corpus and I do this dependency parsing, which will give me a huge structure in the end, let's say if I have a huge corpus. And then I want to identify which of these relations are actually meaningful for the domain that I'm analyzing. Do you think that these methods can be of help?
So I think the question was, I want to build an ontology, which is kind of a hierarchy between words or concepts, and can I use parsing for that, or dependency parsing? And the answer is yes and no. So yes, you can, but it will be a very first step. So like you have to have some more work to do, like to actually build this ontology, but I do agree that building it will be much easier if you start from parse trees than if you start from like sequences of words, right? So these relations are definitely useful, but they're a first step, and you need to know like what you actually want to extract and how to, have your system do it. So we can talk later if you want on the details, but like it's definitely a good first step. You'll have to, it's a research work.
Yes, thank you.
Anyone else?
Thank you for the talk.
I cannot see because there's some projector on. Wow. Okay. So I cannot see what I can hear. Let's try.
Thank you for the talk. I just wanted to ask if it would be possible to use generative adversarial networks to build parser. I was just thinking by myself to have, for example, a generative model to build different trees, and then a discriminative model to learn to choose a good one.
Well, I'm not saying that you cannot do it. I'm not sure it's the best approach to do it. So if you have like parse trees with like annotations, then there is no reason to use GANs. Like just you can use the annotations. If you don't have annotations, maybe you do want to use some kind of more an approach which is kind of more semi-supervised. But I would, I think there are easier ways to do it than GANs. But if you want to try, then yeah, sure, and maybe proven wrong. Okay. It could work.
Thank you very much.
Okay, any further questions? I have one short question. For a while, these two approaches to parsing, transition-based parsing and graph-based parsing, which was looking for a more global solution, but could not condition on history as much as transition-based parsers. They were kind of competitive to each other. So recently, transition-based parsers became much better because we now have much better mechanisms for representation learning, so we can have a very good representation of the input, and that helps a lot. But do you think that the traditional problems like error propagation and label bias are still an issue, or they don't matter that much anymore?
Okay, so the question was, in the like a few years ago, graph-based parsers were much better than transition-based, like the good ones, and now they kind of caught up because of LSTMs and so on. And do we still have the kind of problem that we had before with this parser, which was basically that we don't know the future and we may propagate errors. So like the kind of problems with greediness. So the answer is first, yes, greedy parsing still hurts you to some extent, but less because you're now much better. We do know that if you use dynamic oracles, which is a way to kind of handle error propagation to some extent, we do get a better parser. That's work with Graham and Chris. Oh, no, not Graham, Miguel, right? Yeah. So with Miguel and Chris. So we do have like, we do show that we can kind of fight it to some extent. So it definitely affected the parser, now it does it less. But we actually also look at the future to the end, so the parser is much easier for it to learn. Label bias, I don't think ever was a real problem. It was kind of just something that you talked about. But definitely error propagation happens and can be reduced. And right now, both transition and graph parser are kind of really improved, and they are still tied, and still I think the graph is a tiny bit better for English at least. But yeah, it's still kind of, they're the same in the accuracy, but like different in the results. So they capture different things.
Thank you very much. Let's thank again the speaker.
Thank you.